Okay, so some more information is coming through about the Beirut explosion, but it looks as if there was 2,700 tons of ammonium nitrate. And so devastation, that is just surprising. It wasn't, the death toll wasn't higher. Because looking at these, looks like apartment buildings or maybe these are commercial buildings. Wow. But unfortunately, it's big. Maybe it's going to climb. But yeah, that's a massive explosion. When you see this cloud, do you see that cloud there? This orange cloud, orange smoke. Orange smoke, that's going to be an indication of, nitrate fire. Probably seen here. Nitrates, this is NO2. I'm giving you that orange smoke. So nitrate fires are very dangerous. Like in China, I think most of I think it was about 300 dead, but most of those deaths were firefighters trying to put out the fire. You got a nitrate like this. In China, I think in China they had nitrate, potassium nitrate. It wasn't ammonium nitrate, but the fuel was, they had cyanide, sodium cyanide, and potassium nitrate. If you have cyanide, cyanide is a fuel, nitrate's an oxidizer. In this case, it's ammonium is the fuel. Now, if there's other fuels around that are even better than ammonium, then that would help. Because ammonium nitrate, I think it's hard by itself to get it to detonate. But if there are other fuels around, because ammonium nitrate, it's locked in the lattice, and so it has to get very hot. But even if it gets very hot, there have been some studies showing that, that's a unique set of conditions that'll cause it to detonate. And it's hard to predict because that's why people just try it and see what happens by experimentation. And so, that's the skeleton kind of redox method. You just mix it and see what happens. But this is pretty devastating for sure. It was a massive explosion. Okay, we'll go on here talking about where we left off last time. And that is, we need to go back through the rest of those homeworks. Okay. So we're looking at the gases, liquids, solids. Classify each of the following statements as true or false. Intermolecular attractions are stronger in liquids than in gases. That's true because the liquids the molecules, the particles of liquid have to stick together. In gases, they're broken apart. And so, room temperature, if you have a liquid, they're sticky. So the intermolecular attractions are stronger than what we call kinetic energy. Kinetic energy would be the temperature. And so the intermolecular attractions being stronger than temperature, kinetic energy holds the molecules. But if they're weak, then the kinetic energy is going to break them apart. So the temperature is. So it's a comparison between the kinetic energy and the strength of the intermolecular attractions. So at a given temperature, a liquid would be stronger than the gas. Both of these have to be at the same temperature for fair comparison. Substances with weak intermolecular attractions generally have low vapor pressure. Oh, did I already go through this? That question sounds familiar, but I don't think I went through this. But this question came up earlier. Substances with weak intermolecular attractions have high vapor pressure. They're easy to vaporize, and so that's false. Liquids with high molar heats of vaporization usually are more viscous. That's true. because stronger intermolecular attractions. A substance with a relatively high surface tension usually has a very low boiling point. That's false. If it has high surface tension, strong intermolecular attractions are making it difficult to break the surface. It's called strong cohesive forces, making it difficult. And so strong cohesive forces means high boiling point. All other things being equal, hydrogen bonds are weaker than induced. No, hydrogen bonds are the strongest, all other things being equal. Induced dipole forces become very strong between large molecules. Yes, that's true. Maybe I did go through this already. Other things being equal, nonpolar molecules have stronger intermolecular attractions than polar molecules. That's false. If we have dipole attractions, that helps. A permanent dipole versus instantaneous dipole, permanent dipole is usually better for small molecules. That's what they mean by other things being equal. Other things being equal are small molecules. That's what we're talking about. The essential feature of dynamic equilibrium is that the rates of opposing changes are equal. That's true. It's a dynamic, and so there's change at the particular level. It's equilibrium at the macroscopic level, and so that means the opposing changes are equal. Equilibrium vapor pressure depends on the concentration of the vapor above its own liquid. Yeah, the higher the concentration of vapor, the more pressure. So it's true. The heat of vaporization is equal to the heat of fusion, but with opposite sign. No, I already did go through this. But maybe I didn't make it all the way through. Vaporization and fusion are two different. Vaporization and condensation would be opposite. Fusion would be freezing, would be the opposite. The boiling point of the liquid is a fixed property of the liquid. Oh yeah, now I remember. I did go through this. Now the boiling point of a liquid is a fixed property. You know, we always know that water boils at 100 degrees C under normal atmospheric pressure. Now, if you change the pressure, obviously it's going to change the boiling point, but it's fixed. That's how we recognize what water is. And so I answered this one true. But I'm thinking in terms of the vapor pressure curve. You know, we can predict the boiling point of water at any temperature. At any pressure. We can predict the boiling point of water for the top of Everest because it's fixed. You know, it's fixed given what the external pressure is. But they called this one false because it changes depending on what the external pressure is. Yes, it does change depending on what the external pressure is, but we know exactly how it changes because it's a fixed property of water. And so this one I didn't like the phrasing. If you shatter an amorphous solid, it will break in straight lines. But if you break a crystalline solid, it will break in curved lines. No, when you break a crystalline solid, like salt crystals, it breaks in straight lines. Those are called cleavage planes. What glasses do, or amorphous solids, is they do a conchoidal fracture. And so, and that's because of the, here. Conchoidal fractures are like this. Conchoidal fractures are when glass breaks. You know, it's just because of the random structure. Whereas in a crystalline, you know, we get very nice, clean fractures, like in fluorite, halite. Halite's table salt, calcite. This is calcium carbonate. These are the mineral names for. So mineral name for sodium chloride is halite. Calcium carbonate is calcite. But these, when you break these, they form little crystals, the same shape. But because of the amorphous nature of, the conchoidal, this would be an amorphous structure, conchoidal fractures. We have two different types of quartz. We have quartz glass and quartz crystal. And they fracture differently. This would be quartz glass, but quartz crystal is different. That's false. That's backwards. Ionic crystals are seldom soluble in water. That's false. Most ionic crystals are soluble, except the ones that have very strong ionic bonds, like +2, -2, +3, etc. Molecular crystals are nearly always soluble in water. That's false. Molecular crystals, a lot of them are made up of non-polar molecules, like wax. Well, the wax is semi-amorphous sometimes, but molecular solids, we should say molecular solids, because um, most molecular solids are crystalline because the molecules can pack, but if you don't give them enough time to pack properly, then they'll end up being amorphous. So molecular solids are nearly always soluble in water. Well, no, that's false, because wax is not. And there are lots of examples of molecular crystals that are not soluble in water. Sulfur. But there are lots of examples of molecular crystals that are soluble in water. Ice, you know. The numerical value of heat, this relies on the solubility rule, like dissolves like, you know, for molecules. Like molecules dissolve like molecules. The numerical value of heat of vaporization is always larger than the numerical value of heat of condensation. No, they're exactly the same. It's just one is you have to add heat, that's vaporization. The other, you have to remove heat, that's condensation. The units of heat of fusion are joules per gram degree C. That's false. The units, heat of fusion is melting, so it's joules per gram or joules per mole. This degree C is specific heat, you know, when you're heating and cooling. When you're melting something, the temperature never changes, so we don't need the temperature there. The temperature is fixed at the melting point. And so we have to be at the melting point in order for the heat of fusion to be valid. The temperature of water drops while it is freezing. That's false. That when something freezes, it stays zero. Once it's all frozen, then the temperature can drop if you just continue removing heat from it. Specific heat is concerned with a change in temperature. That's true. We're very interested in cooling and warming. Specific heat is for cooling and warming objects. Identify the intermolecular attractions in methanol and fluoromethane. Which of the two substances do you expect will have the higher boiling point? Methanol. Methanol for sure, because hydrogen bonding, you know, you see, and they're both about the same size. This is dipole, you know, it's a very big dipole, but it's not as big of a dipole as this because of the partially exposed proton in hydrogen, you know. It's what we call de-shielded proton. Which of the two substances do you expect will have a higher boiling point? Methanol. Which will have a higher equilibrium vapor pressure? Fluoromethane should have a higher equilibrium vapor pressure. The lower the vapor pressure, the higher the boiling point. Both molecules have induced dipole. So both molecules have, you know, induced dipole, that is instantaneous induced, that is dispersion forces. Dispersion forces are present in everything. So that's a give me, you know, you're always going to have dispersion forces if it has electrons, because electrons can move to one side and increase the polarity of the molecule for an instant of time. But methanol has hydrogen bonding and fluoromethane does not. The molecules are about the same size. So under what circumstances might you find that a substance having only induced dipole forces is more viscous than a substance that exhibits hydrogen bonding? When we're comparing molecules of different size. So if you look at wax, what holds the wax molecules together? What holds the wax molecules are just hydrocarbons, big hydrocarbon molecules. And so what holds them together are induced dipole. But, you know, the melting point of wax is kind of high compared to the melting point of some methanol. Methanol is a liquid, you know, at room temperature. So methanol is actually a very low melting point, whereas wax is much higher melting point. But methanol has hydrogen bonding. Wax does not have hydrogen bonding. The difference is wax is a gigantic molecule, whereas methanol is a tiny molecule. And so when they're this is what they mean, all things being equal, you know, we're comparing things of the same size in the same numbers. And so we can have induced dipole forces. Think of asphalt. Asphalt is also a hydrocarbon. You know, if you go out in the street and you try to melt the street, you know, what kind of temperatures do you need to melt the street? You need very high temperatures because those molecules are very, very big. Those very big molecules have very big induced dipole forces, which means they have very high melting points, much higher than water. You know, water melts at 0 degrees C, but the asphalt in the street melts at a much, much higher temperature. You need a torch to melt the asphalt in the street. So large molecules can have much stronger forces than small molecules with hydrogen bonds. A liquid in a beaker is placed in an airtight cylinder. The liquid evaporates until equilibrium is established between the liquid and vapor states. The piston in the cylinders suddenly adjusted to reduce the volume of the cylinder. If there's no change in temperature, what changes will occur, if any, in the rates of evaporation and condensation? Well, so we can, this is something where we perturb, you know, something that's at equilibrium. And so if this liquid is at equilibrium and then there's some kind of a piston here, a piston just means it has an adjustable volume. So this piston here, lid, can move up and down depending on, you know, what's going on in the chamber here. And so if we put some liquid like water, let's throw in some water in here, liquid water, then some of that is going to vaporize. Initially, if this is dry, then we have net evaporation. But as we get more and more molecules, water molecules in the vapor state, then some of those will collide with the liquid and stick. You know, water molecules are somewhat sticky because of the hydrogen bonding. And then we'll reach a point where the rate of evaporation is equal to the rate of condensation. And so then we're at what we call dynamic equilibrium. Dynamic equilibrium means these are just cycling. The water molecules are cycling, going in circles, from liquid to salt and gas, back to liquid, etc. But nothing's changing. There's no net change. Nothing's changing macroscopically. This is saturated, so this should be at 100% relative humidity inside the container here, what we call the head space or the gas space up here. Now, if you compress this cylinder, you know, then that's going to increase the pressure, obviously. If it increases the pressure, then there's going to be more collisions for the gas. So, well, if we have more collisions, then that's going to increase the condensation rate here. And so by compressing this, you're going to get more collisions. And more collisions means more condensation. The evaporation rate stays the same. You know, the evaporation rate only depends on the temperature. And the condensation rate should go up. And what's going to happen is eventually it's going to reestablish an equilibrium. The equilibrium is going to just be based on, you know, so the condensation rate kicks up and eventually it's going to go down as the number of gaseous molecules goes down, and we're going to reestablish equilibrium. And the new equilibrium is just, it's going to be a smaller space here, but it'll be at the same pressure as it was before, you know. And so it'll be at the same pressure. So let's see what their answer says. The reducing volume increases vapor concentration, which causes a temporary increase in the rate of condensation until equilibrium is once again established. Evaporation rate, which depends only on temperature, is not affected. Okay, that's fine. Three closed containers have identical volumes. A beaker containing a large quantity of ether, a highly volatile liquid, is placed in container A. It evaporates until equilibrium is reached with a substantial amount of ether remaining. A beaker with a small amount of ether is placed in container B. The ether all evaporates. A beaker with an intermediate amount of ether is placed in container C. It evaporates until it reaches equilibrium with only a small amount of ether remaining. Compare the final ether vapor pressures in the three containers. Well, container A and container C should have the same, because it's saturated. Once it becomes saturated, we can't evaporate anymore. But container B may or may not be saturated, because all of it evaporated. If all of it evaporates, it could have saturated and we just don't have any excess liquid left over. So it could have been just the perfect amount to saturate it, or it could result in something that's unsaturated. Like if you spill some water on your table, it's all going to evaporate, but it's not going to saturate your dining room or kitchen or whatever with water vapor, because it just wasn't enough. And so A and C should be the same. Container B should have the lowest. Well, it depends, if it didn't have, if the spilled liquid wasn't enough to saturate it, then yeah, it'll have a lower vapor pressure. But it's not totally clear. It could have completely evaporated, like I said, and saturated it. The equilibrium vapor pressure of water at 24 degrees C is 22.4 torr. A sealed flask contains air at 24 degrees C and 757 torr, and a glass vial filled with liquid water. The vial is broken, allowing some of the water to evaporate. What is the maximum pressure the system can reach? All right, so this is kind of weird question. All right, this has got to be dry air. So we're going to make an assumption. Sometimes if it's not clear a problem, you always have to make an assumption. So sealed flask contains, we're going to assume it's dry air. Well, even if it's wet air, we need to know what the relative humidity is. Is the relative humidity 100%, then that means it's saturated. But we're going to assume that it's dry air, 0% relative humidity. There's no water in the air. Okay, and it's at 757 torr. So we have a 757 torr of dry air. And then they put a vial in there filled with water. And we're going to assume, the next thing we're going to assume is that there's enough water to saturate, allowing some, they said some of the water to evaporate. So that means it's saturated because not all the water evaporated. If all the water evaporated, then it might not be saturated. Okay, so that means we have 757 torr of dry air plus 22.4 torr of the water. The water is going to evaporate to saturate it. When we saturate it, it's going to generate 22.4 torr, regardless of the size of the container. A bigger container means more water has to evaporate to saturate. A small container means less water has to evaporate. But we have enough water to saturate the whole container. So if you're looking in your, let's say a room, and you spilled a little bit of water, that's a different story than having a vial filled with a little bit of water. For a room, we need a lot more water to saturate it than a little vial or a container, sealed flask. Sealed flask, we don't need that much water to saturate it. So yeah, 757 plus 22.4 gives us 779 torr. This is Dalton's law, by the way. Questions 106 and 107 are based on the apparatus shown in 1544. Study the caption that explains how vapor pressure is measured and then answer the questions. Measurement of vapor pressure. Initially, the flask contains the liquid whose vapor pressure is to be measured. The flask tube's manometer above the mercury in the right leg are all at atmospheric pressure. The mercury in the left leg of the manometer is also at atmospheric pressure. So the mercury levels are the same in the two legs. To measure vapor pressure, evaporation occurs until equilibrium is reached. Vapor causes the increase in pressure to be measured directly. Okay, So here, none of this is vaporized, this volatile liquid. So they just put in the liquid in here. But before they put in the liquid, it was all uh, the same weights. In other words, the same pressure inside and the same pressure outside. And then they let this vaporize and saturate the air in the glass. And that's going to change the pressure. Well, it's going to change the pressure by this much. And so this is the vapor pressure at that temperature. And so this is an easy way. We can just measure how many millimeters mercury difference that is. And that's the pressure, the vapor pressure. Assume you're about to use the apparatus to determine the equilibrium vapor pressure of volatile liquid. Would you expect the vapor pressure shown by the manometer to increase uniformly until equilibrium is reached? Yes. You know, this should evaporate, you know, and as it evaporates over time, this should increase uniformly, you know. And so, yeah.
Professor?
Yes.
Someone is asking on Piazza about the Zoom link.
Oh my God. All right. I forgot about Zoom link again. Shoot. No wonder. Invite link. So, thanks for reminding me. I don't know why I didn't get an alert. I guess I don't get an alert because of Zoom. When I have Zoom on, all my alerts are turned off. Did this link work here? You know, Zoom changed the security protocol, so I don't know if the old links work. They used to work, so there was just only one link. I always had the same link. But then they're trying to keep people out, like uninvited people out, and so they changed the way they might have changed it. How it worked. Okay, let's give it a minute here. Okay, yeah, sorry about the Zoom link there. Let me, if anybody else has joined. I lost them. Okay, again, sorry about the Zoom link there. I had covered some of the homework problems in chapter 15. In fact, still going through the remaining homework problems in chapter 15 here. And so that's for the first 25 minutes of class. So check the recordings to see the discussion of the homework there. I need to post yesterday's and Monday's recordings as well. So I'll post those on YouTube, or you can access those on Canvas. So we're looking at this problem here based on this. This is an apparatus that we can use to measure the vapor pressure of volatile liquids, or vapor pressure of liquids. It doesn't have to be volatile, it just has to be any liquid. And the liquid, what it's going to do is it's going to vaporize, and it's going to push the mercury down on this side. It generates vapor, so it pushes mercury down. How much it pushes the mercury down is the vapor pressure in millimeters of mercury here. Now I see the problem. There's a choice, A, B, or C. Increase rapidly at first, then slowly as equilibrium is reached. Yeah, this seems more appropriate. The rate of evaporation is constant. You know, it's just going to continue to evaporate. It just depends on the temperature. Now, the rate of condensation is going to start off slow because there aren't that many molecules initially here. Very few molecules means we're going to get very little condensation. But the rate of condensation is going to increase as we get more and more molecules. And so there's not much condensation there to begin with. So evaporation increases rapidly at first and then slowly. This should be the answer here. Increases slowly at first and rapidly, no, this is wrong. And so this is it's the correct answer. You read through this. Suppose that all of the liquid initially introduced to the flask evaporated. If all of the liquid in here evaporated, then we don't know if it's saturated or not. Did we add enough to saturate it? Maybe we needed a little bit more. You know, if there's liquid left over, then we know it's saturated because no more liquid was evaporating net, you know, at the macroscopic level. And so this throws up a big question. Why and how could this occur? Well, you didn't add enough liquid. And explain in terms of evaporation and condensation rate. Well, this one, we don't want to get into it too much more. You just need to add more liquid. An industrial process requires boiling a liquid whose boiling point is so high that maintenance costs on associated pumping equipment are prohibitive. Suggest a way that this problem might be solved. Yeah, one way this problem can be solved is what I used to use a lot in the lab. You know, you have pressure cookers. Pressure cookers are when you want the temperature to go up, you know, and you want the temperature to go up so your food cooks faster in a pressure cooker. But sometimes you don't want the temperature to go up. Sometimes you want the temperature to go down. And so I use this piece of equipment in the lab all the time, and that is a vacuum oven. A vacuum oven, let's say if you throw your clothes in a clothes dryer, you know, the temperature has to be pretty hot in order to dry your clothes because water boils at 100 degrees C, you know, and the closer you get to that, the better, you know, the faster it'll dry. Right? And so you want to dry it at very high temperatures. But if you dry everything at high temperatures, what's going to happen to your clothes? You know, your clothes are going to get cooked at high temperature and they aren't going to last as long. Well, that's what happens to chemicals. Some chemicals are very temperature sensitive. So if you're going to dry a chemical and you don't want to cook it, you know, then that could be a problem. Some organic chemicals decompose at very low temperature. And so for temperature sensitive chemicals, I always dried them using a vacuum oven. Because let's say you could cut the atmospheric pressure in half. If you could cut the atmospheric pressure in half, then water boils at like, you know, 80 to 90 degrees Celsius. And so if the water is boiling 80 to 90 degrees Celsius, then you don't have to get it nearly as hot to dry it. And so if you could cut it down to 1/3 an atmosphere, you know, we can get a decent, you don't need a very fancy vacuum to get it to 1/3 of an atmosphere, you know. In fact, you know, you could get water to boil at room temperature. Have you guys seen that? You could use just a simple hand pump to get water to boil at room temperature. And that way you don't even have to heat it. You can dry your clothes at room temperature if you had a strong enough vacuum. Now, you aren't going to be hand cranking a vacuum at your clothes dryer or at a clothes dryer, you know. And so let's see, water boiling at a room temperature. And we're going to use a hand crank vacuum, hand cranked vacuum. So which one was it? Yeah, hand powered vacuum, this one. I guess there's no audio on this. So they have a little flask of water in there. This is a little bell jar or a jar. This is just a jar. Should be thick walled glass for a vacuum. This is going slow. Let me speed it up here. Okay, so the water's boiling. There's no heat there. This is boiling at room temperature here. Why don't they show the vacuum? Let's see the vacuum. There's one where we can actually see the vacuum. Maybe this is it.
In this demonstration, I am taking.
Let me fast forward it.
System. Actually falling a little bit. You used to say, well, why is it?
All right, you can hear the vacuum pump in the background. So they're using a mechanical electrical vacuum pump for that. You don't need that powerful of a vacuum to do this. You know, $50. This is a more expensive one. Oops. All right, this was the one I was looking for. There's an Erlenmeyer flask filled with water. And so this person has a hand crank vacuum pump. It's creating a low enough pressure, you know, to get the water to boil room temperature. The vacuum oven that I used didn't have that powerful vacuum. You didn't really need it. The vacuum pump I used, the water boiled around 60 degrees Celsius, just fine. And then you can dry things. I never heated it up to 60. You know, I'd heat it up to like 40 degrees Celsius or something like that. And things would dry very rapidly in there. And that's easy to predict because of water's vapor pressure curve. You know, this curve here. This curve here is defined by mathematical equations, so we can calculate the boiling point of water at any temperature. So at room temperature, what kind of vacuum do you need? You need about like 0.03 atmospheres, you know, which is pretty far down there. This curve doesn't go far enough. Vapor pressure curves are also given in tabular form. In tabular form, it looks like this. And so if you take all these numbers here and make a graph, the graph looks like what I just showed you there. And so this is a table of water vapor pressures. And so at 25 degrees C, water will boil at room temperature if the external pressure is 23.8 millimeters of mercury. And so we need a vacuum that gets it to 23.8, you know. In our lab, the water boiled around 60, so the vacuum was around 100 torr. Around 100 torr, you can buy an inexpensive pump that'll do that. Thing was, we had to use inexpensive pumps because the pump would be pumping, you know, a lot of water vapor. We have to trap the water vapor before it gets into the pump, because if the water gets in the pump, it could destroy the pump. Liquid water gets in the pump, it will destroy the pump. So the liquid can be boiled by reducing the pressure and thus the boiling temperature. A calorimeter contains 72.0 grams of water at 19.2 degrees C. A 141 gram piece of tin is heated to 89.0 degrees C and dropped into the water. The entire system eventually reaches 25.5 degrees C. Assuming all the energy gained by the water comes from the cooling of the tin, no energy lost to the calorimeter or surroundings. Calculate the specific heat of tin. And so this is a standard, what we call calorimetry problem. This is a standard problem like in Chem 1A. You do this style of problem. It's a very common problem. In calorimetry, what we're going to do is we're going to let the calorimeter, you know, the calorimeter is the water, basically, absorb all the energy here. So it can get more complex. And so what we're doing in this particular problem is we have a 72 grams of water here. 72.0 grams of H2O liquid. And the temperature of the H2O liquid is at 19.2 degrees C. So starting out 19.2 degrees C. And then a 141 gram piece of tin at 89 degrees C. So we're going to have a hot piece of tin up here. So this is SN solid, 141 grams at 89 degrees C, 89.0 degrees C. So hot piece of tin, and then we're going to drop the tin inside the water. And so what's going to happen, and when we drop the tin inside the water, the tin is going to cool down and the water is going to warm up. And they're going to reach the same temperature, actually. The yellow. They're going to end up at the same temperature. Something here. And the same temperature is going to be, we're going to have the chunk of tin sitting in here. So that's going to be the tin solid. And we're still going to have the H2O in here. And they'll be at the same temperature. And so what is that temperature? 25.5 degrees C. And so both the tin and the water are 25.5 degrees C. All right. So what happened? Well, the water warmed up from 19.2 to 25.5, and the tin cooled down. Now, there's something called the first law of thermodynamics, which I talked about before. The first law of thermodynamics just states that energy is conserved. Energy is conserved. And so what that means is that the energy, the tin cooled down. So tin cooled down. So lost energy. Well, that energy wasn't really lost. That energy had to go somewhere because energy is conserved. It's neither created nor destroyed. And so if tin cooled down, it lost energy. Who did it lose the energy to? Well, the H2O. The H2O warmed. And if the H2O warmed, it gained energy. And in fact, it had to gain the exact same amount of energy that tin lost, because we can't have energy just disappear. And so in other words, the heat that tin lost is equal to the heat that water gained. And so the heat that tin lost is equal to the heat that water gained. Well, they're opposite signs. So if tin loses heat, it's negative. If the water gains heat, it's positive. So to make these equal, I have to change the sign on one of them to make it equal, because they're going to be opposite in sign. So this negative is just to change the sign to make them equal. That is, the heat Q that tin lost is equal to the heat that water gained, because energy can neither be created nor destroyed. So this is a statement of the first law of thermodynamics here. So how much heat did tin lose and how much heat did water gain? Well, the heat that tin lost, it's an object that cools. So it's going to equal M, the mass of the tin, times C, the specific heat of tin, times delta T of tin. And how much heat did water gain? Well, that's going to equal the mass of H2O times the specific heat of H2O times delta T for H2O. So we have all the numbers here. We could look up the specific heat of tin, but that's not the purpose of this problem. The purpose of the problem is not to look up the specific heat of tin, it's to calculate the specific heat of tin. So in order to calculate the specific heat of tin, we're going to leave the tin as our unknown, although it's easy to look up because it's in the table here. But let's see how it compares. And so we're going to solve for this, the specific heat of tin. All right, so the specific heat of tin is going to equal the mass of H2O times the specific heat of H2O times delta T for H2O divided by the mass of tin and divided by the delta T of tin. And so let's just plug in the numbers. The mass of the H2O is 72 grams, so 72.0 grams. I'm not going to label this H2O because the units aren't going to cancel, you know, because this is mass of H2O, this is mass of tin. So I already know they aren't going to cancel properly, but it's okay. It works in this case. It works because the unit. Well, actually, I can put in. I'll just put it in here and let's see what happens. 72.0 grams of H2O. The specific heat of H2O, everybody should have that memorized. It's 4.18 joules per gram degrees C. Is per gram of water. degree C of water. And so this is only good for water. So it's only good for water. I'll put H2O on the outside. That restricts it. And then what is the delta T for the water? Delta T for water is the final temperature, 25.5, minus the initial temperature, 19.2 for water, and that's degrees C. And so this actually works out the units here. The units would be grams of H2O, you're going to cancel out grams of H2O. Degrees C change for H2O cancels that, and that just leaves us with joules here. Okay, on the bottom, what do we have? So this is going to be divided by the mass of tin. The mass of tin is 141 grams of tin times delta T of tin. Delta T of tin is going to be the final temperature, which is the same, 25.5, minus the initial temperature, 89.0 degrees C. And so let's go ahead and calculate the numbers here. At 25.5 minus 19.2 equals times 4.18 times 72 equals divided by 141. And so actually the top is how much heat the water gained. The water gained 1,896.04 joules, 048 joules. That's the amount of heat water gained, 1,800 on the numerator. Then I'm going to divide it by 141 grams. That's the heat that tin lost. And the amount of tin we had was 141 grams, and the temperature change for the tin was it 25.5 minus 89. Oops, you know what? Remember I said about the negative sign? If you don't keep track of the negative sign and the positive sign, it screws things up. And I'll show you what I mean in just a second. So 25.5, so divided by, and put that in parentheses, 25.5 minus 89, close parentheses. There's a minus 63.5. The tin lost 63.5. All right, and this gives me a minus 0.2117 joules per gram of tin per degree C. And so I'll just put this in parentheses, call it for tin solid. Now, having a negative specific heat is weird, because if you have a negative specific heat, that means it just gets hotter, you know, just sitting there. And so it's like if you had a negative specific heat for your coffee is just getting hotter rather than colder. And so this doesn't make physical sense. It doesn't make physical sense because I forgot to keep track of the sign. You see the sign here is negative. I was supposed to make this negative here. This whole thing should have been negative here. That means this whole thing should have been negative here. And then the negative times divided by negative should have given me a positive here. So when we get to Chem 1A, we have to keep track of this sign. Otherwise our calculations, because our calculations get more complex. In Chem 4, I know he didn't really keep track of sign much, and he didn't really keep track of lost or gained either. But you can't do that in Chem 1A. In Chem 1A, we got to keep track of these types of things. Otherwise our number is going to be way off. If I got a negative here, it's a ridiculous specific heat. It doesn't make physical sense. And so we need a positive here, and we get a positive if I just carry the sign down here. And so 0.2117, well, we can compare that with what the book has in its table. The specific heat is in our book for tin. And so tin, oh, actually, wow, ST, tin is missing. All right, that's good. Specific heat of tin is not in our book. I thought it would be in our book because tin is such a common metal. They got 0.21 joules per gram degree C. Okay. 110, a 54.1 gram aluminum ice tray in a home refrigerator holds 408 grams of water. Calculate the energy that must be removed from the tray and its contents to reduce the temperature from 17 degrees C to 0 degrees C. Freeze the water and drop the temperature of the tray and ice to -9 degrees C. Assume that the specific heat of aluminum remains constant over the temperature range involved. So this is kind of a mixture problem here. We got lots of mixture problems in the advanced, you know, usually the advanced challenge problems. These are challenge problems. But we in this case, we could treat the mixture separately. For example, the 54.1 grams of aluminum, you know, what are we doing with that? And so we could treat it separately here. And so the aluminum ice tray is going to go from 17 degrees C to 0 degrees C, and then from 0 degrees C to -9 degrees C. Well, nothing really happens because aluminum is a solid and there's no phase change. And so really all we're doing is we're cooling the aluminum from 17 to -9 degrees C. And so here, the 54.1 grams of aluminum is being cooled. So here's our aluminum ice tray. 54.1 grams of aluminum solid.
Sir?
Yes?
It's break time.
Oh, is it break time? All right. All right, we're gonna take a break. We'll take a break for 15 or so minutes, maybe more. Let me see. Okay, again, sorry about the Zoom link. I forgot to post that, but check out the recording. It'll have just I just have been going through chapter 15 homework. It's a continuation from yesterday. Okay, so check out the recording for that. You can pause the recording here. But let's take a look at this problem again. We have 54.1 grams of aluminum. And that aluminum is going to be cooled to 0. It's going to stay at 0 for a bit while it waits for water to freeze. And then once the water freezes, then it's going to go back down to -9. And so we'll just start here from 17 degrees C. And then we're going to cool it all the way down to -9 degrees C. And so overall, that's what's going to happen. The amount doesn't change here. Now the water, it's going to have 408 grams of water. So there's 408 grams of H2O liquid. Now the H2O liquid, we can't go all the way down to -9 degrees C, because what's going to happen is we're going to start off at 17.0 degrees C, and then this has got to cool to 0 degrees C. And so we're going to have at H2O liquid at 0 degrees C here. And then what we're going to have to do is we're going to have to freeze it. And so freezing it, we're going to go from H2O liquid at 0 degrees C to H2O solid at 0 degrees C. And then once we freeze all of the water, then we can cool it all the way down to -9 degrees C. So we're going to have H2O solid at -9.0 degrees C. So our freezer has to do this. Our freezer has to cool down that much aluminum, plus it has to cool down the water, freeze it, and then cool down the ice. And so this will be Q for the aluminum. The Q is the heat that we have to remove. This is going to be Q for the H2O 1. This is going to be Q for the H2O 2. And Q for H2O step 3. 3 steps here for the liquid water. Now the aluminum is just an object cooling, so that's just equal to mass mc delta T. And so what is the mass of aluminum? It's 54.1 grams. C, the specific heat for aluminum, did they give it to us? No, they didn't give it to us in the problem, so we have to look it up in the book. And so take a look for that book here. .90 joules per gram degree C. So the specific heat of aluminum, .90 joules per gram degree C. This is only valid for aluminum solid. Times our delta T. Our delta T is going to be our final temperature minus 9.0 minus the initial temperature, which is 17.0 degrees C will be the units. And so altogether 26 degrees C temperature drop. And so how much heat had to be removed for the aluminum to cool down? And so it's 54.1 times 0.9 times negative 26. And so it's probably easiest to do this in kilojoules because I come out to 1,265. So I'm just going to say 1.265 negative kilojoules. So the negative sign tells me that the freezer has to remove that amount of heat to cool this aluminum tray down. Now for water, we have to do multiple steps for water here. The first step is just to cool the water down. So cooling the water down is just mc delta T. So the mass of water in this case is 408 grams. C, we should have memorized, is 4.18 joules per gram degree C. Delta T is going to be T final minus T initial. So 0 degrees minus 17 gives us a minus 17.0 degrees C temperature drop. And so what does that come out to? So the first step of this is going to come out to 408 times 4.18 times minus 17. And so this gives me minus 568. Minus 568. We're allowed 3 sig figs, 568.4 joules. So I have a mismatch in the units here. Maybe I'll go with joules or kilojoules. We'll see. This is going to be 0.5684 kilojoules negative. And so to cool the water down, we have to remove about 0.6 of a kilojoule worth of heat. How much is it going to be to freeze the water? And so let's see how much energy we need to freeze the water. So for freezing the water, which is step 2, it's equal to m delta H. That's because delta H is given in units of mass. So it's mass times delta H. And so the mass of water we have is 408 grams. And our delta H value, we have to look that up. This is delta H of freezing. So it's delta H of freezing, which is the opposite sign of delta H of fusion. So we're going to look up delta H of fusion, and which is, I think, 333. Let's take a look. Yeah. Delta H of fusion for water is 333. So we'll use that. That's fusion, so freezing's negative 333. And so we're going to put in negative 333 joules per gram. And so how much energy does it cost to do it? Well, it's going to be 408 times that, 408 times 333. I'm going to do this in kilojoules. Probably want to do it kilojoules. It's going to be negative 135.8. We're only allowed 3 sig figs here, kilojoules. And so cooling the water didn't take that much. We had to remove about 0.6 of a kilojoule, but to freeze that water, it's like 136 kilojoules we'll have to remove. So freezing it by far is taking the most energy here that needs to be removed here. Now, what about cooling the ice down? How much energy does it cost to cool the ice down from 0 degrees to -9? So that's cooling ice, so that's MC delta T. Okay, so what's the mass of ice? Well, the mass doesn't change, it's 408 grams. We need the specific heat of ice though, and so we'll have to look that up in a book. That one you don't have to memorize, just water. And so if we look at the specific heat of ice, which is solid, 2.06 joules per gram degree C. So just leave it here. This is going to be 2.06 joules per gram degree C. This is for ice. Times the delta T of ice. It's going to be -9 -0. So it's just, we're cooling it by -9 degrees C here. And so how much heat do we have to remove to cool the ice down? It's going to be 408 times 2.06 times 9. And 7,564. So it's going to be negative 7,564, which is negative 7.56. We're allowed 2 sig figs. So we'll just leave it at that, negative 7.56 kilojoules. And so I just did the conversion in my head by just moving it 3 places over. And so altogether, our freezer has to remove about 1,200, I mean, how's that 1.2? About 1.2, 1.3 kilojoules to cool the aluminum, and then 0.6 kilojoules here, and 135, 136 kilojoules, and about 8 kilojoules. So what we're going to do is we're going to just add them all up. Adding them all up. And this one I'm going to be allowed, well, I'm only going to be allowed 2 sig figs on this one. And so I'm going to have minus 1.26 kilojoules. Okay. Plus a minus 0.56. How many sig figs here? I'm allowed 3 sig figs here. So plus a minus. So minus 0.568 sub 4 kilojoules. And then this step here is going to be minus 135. I'm allowed 3 sig figs here. So minus 135.8 kilojoules. And then this step here, minus 7.56, minus 7.5. This one's 2 sig figs, 7.56 kilojoules. So it looks like we're allowed only no decimal places. We're just allowed the here because then certain digits 10. And so let's go ahead and add these up. So 1.26 and 0.5684 and 135.8 and 7.56. And so the total amount of heat we'll have to remove is minus 145.1 kilojoules, or we're going to have to remove 145 kilojoules must be lost. And it's not lost, the freezer has to take that out and dump it into your room, into your kitchen, is what it's going to do. Let's take a look. Here. Well, what did I do? So they're getting a total of minus 174. I got minus 145. And so I made a mistake somewhere. Let me take a look. So this is minus 1.3, that's right. Step 1 for the water's minus 29 kilojoules. Oh, cooling the water. I must have miscalculated that. Sorry. Because they're getting minus 29 kilojoules. I got minus 0.6 of a kilojoule. Let me see. Let me redo that calculation. So 408. This is what you need to do on exams. You know, if you have time on exams, is you double check your calculations, because you could have miskeyed it like I did. I did miskey it. Sorry. Oh, what I did there. But you could have caught that if you double check your calculations in the calculator. Make sure you didn't miskey it. Oops, this was right. The equation was right. This was wrong here. Undo that. All right. The correct answer for this is 28,992. So it's negative 28.99. We're allowed 3 sig figs, so I'm going to go 28 minus 28.99 kilojoules. And so that changes that one. And so that will mean we're at about 174 kilojoules lost. The others look the same as what they got. So that was my mistake with keying it in the calculator. So again, on exams, if you have time, you always want to double check that you didn't miskey it. All right. Let's go into the next problem here. The labels have come off the bottles of 2 white crystalline solids. You know one is sugar and the other is potassium sulfate. Suggest a safe test by which you can determine which is which. Obviously taste, they're going to taste different, you know, but it depends on how bad potassium sulfate is. Is potassium sulfate generally regarded as safe, or is it toxic? But then you don't want to taste things in lab, because you don't know other students. Are they careful, or are they cross-contaminate things? But if you don't know potassium sulfate, then what we do is we look it up. Whenever we do a lab with an unfamiliar chemical, what we want to do is we want to look up the MSDS or the SDS. MSDS stands for Material Safety Data Sheet, and SDS is just shortened to Safety Data Sheet. All these have to be kept in lab, the MSDS, Material Safety Data Sheet. And every time you buy a chemical, the chemical has to include the MSDS or the SDS. So if we bought a chemical from Fisher Scientific, it includes this, a safety data sheet, potassium sulfate. And so this is included in the box or the packaging. These are other names, dipotassium sulfate. Sulfuric acid is not a name for it. Oh yeah, sulfuric acid dipotassium salt is a name for it. Potassium sulfate 2:1, all right. And then we look, you know, eye contact, first aid measures. Rinse immediately with plenty of water, also under the eyelids for at least 15 minutes. 15 minutes is like the golden number. You know, if you get anything in your eyes, usually 15 minutes is sufficient time to get that. Your eye is like, if you have a dirty sponge and you try to wash it off, if you try to wash off a dirty, wet sponge, how long does it take? It takes a lot longer because, you know, the sponge is saturated with dirty water. So it's going to take a lot longer to flush the dirty water out of the sponge. Well, how long is it going to take? It's going to take about 15 minutes of flushing. Your eyes are like a sponge. And the same thing with your skin. Skin is like a sponge. And so if you have a wet sponge and you're trying to wash off the dirty water that's saturating the wet sponge, it's going to take you at least 15 minutes of rinsing. And so you'll see this a lot, 15 minutes. Skin contact, inhalation, you know, depends on how much you inhale. Ingestion, firefighting, you know, we have to worry. Sulfates can be a mild oxidizer to moderate oxidizer, so. But it shouldn't catch on fire. It's not a fuel, it's an oxidizer. When we have combustion, you know, if it oxidizes something, then it produces oxides of sulfur, sulfur oxides, which are toxic. You gotta watch out. Exposure. Let's see, ingestion, if we can find that. Sometimes they put the LD50. You know, here it is, LD50. LD50 is the lethal dose, potassium sulfate. Lethal dose of potassium sulfate, for if you, whatever your ethics are, this was a lethal dose tested on a rat. And it was 6.6 grams per kilogram of mass. And so let's say you weigh 50 kilograms, then it would be 50 times 6.6. So 50 times 6.6 would be 330 grams. 330 grams would be the lethal dose, you know, for a 50 kilogram person, which is, nobody's going to be eating 330 grams. That's a third of a kilogram worth of potassium sulfate. So it's not very poisonous. That's LD50. LD50 is a statistical thing. It's 50%. 50% of them passed. The other 50% survived. It wasn't 100% lethal at that dosage. You know, it's like the China explosion. Most of the deaths were firefighters. You know, you're a firefighter, you see orange flames like that. You got the same thing. A lot of the deaths, well, not a lot of Texas City. You know, the firefighters were on the dock. You know, when the thing exploded. Watch out. I'm not sure how many firefighters were at the warehouse in Beirut when that, but if you see orange flames like that, that's bad news, especially if, you know, ammonium nitrate itself is a fuel and an oxidizer all in one. You know, I think in the one in China was potassium nitrate. So as long as potassium nitrate doesn't come into contact with the fuel, you're okay. You know, a reducer, you're okay. But unfortunately, I guess it was stored with, you don't, when we store chemicals, we don't store oxidizers and reducers together, you know, otherwise you're going to get a reaction. And so we try to keep them separate. You put all the oxidizers on one side and all the reducers somewhere else, so that they don't come into contact with each other. You can't do that for ammonium nitrate because ammonium nitrate has the oxidizer, nitrate and ammonium in the same compound. So you got the fuel and the oxidizer in the same thing. And so ammonium nitrate doesn't need anything else. know, it's just nitrate's a great oxidizer, but it needs acid. Well, ammonium's an acid. And so ammonium, you know, ammonium isn't the greatest fuel, you know, but it's an okay fuel. But, you know, you need certain things to happen to get it to explode like that. Like the Oklahoma City was ammonium nitrate, but, you know, they put lots of fuel oil in that bomb. And the fuel oil served as a better reducer, a better fuel than ammonium. And so it was a mixture of, I think, fuel oil and ammonium nitrate, which made that explosion much more severe, I think. But you need other things like heat and then moisture, you know, because nitrate needs some acid, and you need, the ammonium will provide some acid and some H+, and so there has to be a confluence of conditions to get it to react in that way. MSDS, of course, is available for all chemicals. So if we looked at the MSDS for ammonium nitrate, you know, that gives us some additional information. So this is Fisher. Let's get a different one. Let's see if we have Aldridge. Aldridge is one of the biggest chemical supply companies in the world, Sigma Aldridge. This is from their catalog. Probably have a link to the MSDS in their catalog. So we could buy this stuff from Aldridge. This is probably high purity. They have different grades of chemicals that you can buy. Say 25 kilograms. What grade is this? This is actually, this is the cheapest grade. This is called reagent grade. Reagent grade is 98% or greater, and so about 2% impurities. But look at the price on that. They were storing 2,700 tons of ammonium nitrate. 2,700 tons is worth a lot of money. 50 kilograms of ammonium nitrate costs $1,440 from Aldridge. I'm sure there are cheaper places you can buy this. Now, if we buy high grade, let's say 99.999% ammonium nitrate, the price skyrockets. Oh, this is biograde, 99.5. Let's look at the price for the higher grade stuff. The higher grade stuff, 100 grams is $224, just for 100 grams. 25 grams is $108. This stuff is expensive. This is high grade, high purity stuff. And so what we want is, let's take a look at the MSDS for this. And so let me see if I can click on the MSDS here. Here's the SDS. And so they changed the name. It used to be called the MSDS, now it's SDS. And so we can see. Actually, I want to look at the firefighting measures, section 5. You know, suitable extinguishing media, dry powder, dry sand, special hazards, NOx, oxides of nitrogen, self-breathing apparatus, etc. They got to talk about other, you know, other things, precautions. So, you know, where does it detonate? Explosive properties, no data available. Wow. Auto ignition temperature, that's, you know, a temperature where it ignites spontaneously without any flame source. Auto ignition, no data available. Oxidizing it, well, it's a powerful oxidizer. Oh, this isn't very useful. I found another paper on ammonium nitrate, but it's a little bit old. I'll share that with you. It's a paper looking at when ammonium nitrate detonates, under what conditions. Those are the conditions, obviously, you want to avoid in these types of situations. All right, that's the SDS. Now let's go back here. So yeah, we don't want to taste it. And so is there another way we could do it? Well, one easy way is melting point. You know, for example, sugar melts at a much lower temperature than potassium sulfate. You know, sugar is a molecular solid, potassium sulfate. So you can melt the sugar and see. That's one way. Another way you could do is, there are a bunch of different things you could do, you know, but melting it might be a safe way. What else? Look, well, the crystals might look similar. Oh yeah, this is dangerous to me. Check for electrical conductivity. It's dangerous because how do you check for electrical conductivity? You put two metal probes in water, you can easily electrocute yourself. We always keep electricity away from water. Pure water does not conduct electricity, but pure water containing electrolytes does. And so the whole conductivity apparatus is very dangerous, I think, because it takes 120 volts AC and puts it there. So it's easy to, if you were to touch the water, you know, solution containing potassium sulfate, you could electrocute yourself. So this is, for me, is kind of dangerous. But that's a way you could do it for sure. Well, what you do is, what's better is not to test for electrical conductivity, is to test for electrical resistance. So if you have a multimeter, you can check for the ohm resistance. You know, if it's non-electrolyte, it should be mega ohms. That's how we check the water. And when I was doing stuff that required high purity water, I always checked the water's electrical resistance. And always made sure that the electrical resistance of the water was in the mega ohm region. If it wasn't in the mega ohm region, then it wasn't pure enough. You know, it had too many salts dissolved in it. And so, but you know, that's easy to do without electrocuting yourself, versus checking electrical conductivity with a light bulb or something like that. The melting point of amorphous solid is not always, the amorphous solids don't really melt. Amorphous solids just soften because of the bonds. Some bonds are weak, some bonds are strong because it's disorganized, the structure. And so what happens at low temperatures, you break the weak bonds, but the strong bonds are still held together. So it just is floppy, gets floppy and softens. So glasses soften. It's called, there's a temperature, which is the glass softening temperature, when glass starts to soften, and it'll get gradually softer and softer, and eventually it'll be completely molten. But that happens over a large range of temperatures. Whereas a crystalline, it's just boom, it's rapid. Without a regular and uniform structure in amorphous solids, some intermolecular forces are stronger than others, or bonds in glasses. The weak forces are easily overcome than the stronger ones. There's a temperature range. You know, weak ones don't require as much temperature. Excuse me. Why does dew form? Dew on a spider web. And so what is dew? Dew is very important. Dew is that condensation. And so there's something called the dew point or the condensation point. And so we should look up what dew, definition of dew is. And so if we look at the dictionary definition of dew, it's a noun: tiny drops of water that form on cool surfaces at night when atmospheric vapor condenses. The grass is wet with dew. So these are the condensation drops. As the temperature goes down, right? Remember, as the temperature goes down, the evaporation rate slows down. And so the relative humidity doesn't stay at 100%, but the humidity, the absolute humidity is going to go down. The absolute humidity goes down because we're not evaporating as much, you know, at night and then during the day. And so that's dew. Dew is important. Let's see what this says. Dew is water in the form of droplets that appears on thin exposed objects in the morning and evening due to condensation. All right. Did donate to Wikipedia some time later. All right. Why does dew? Because the temperature cools down. As the temperature goes down, the absolute humidity is going to go down. As temperature drops, the equilibrium vapor pressure drops. It becomes super saturated, yeah. All right. So I'm spending a lot of time in chapter 15, but these are calculations. These type of calculations are kind of important for preparation for Chem 1A. So it is a hot summer day and Chris wants a glass of lemonade. There is none in the refrigerator, so a new batch is prepared from freshly squeezed lemons. When finished, there are 175 grams of lemonade at 23 degrees C. That is not a very refreshing temperature, so it must be cooled with ice. But Chris doesn't like ice in lemonade, therefore just enough ice is used to cool the lemonade to 5 degrees C. Of course, the ice will melt and reach the same temperature. If the ice starts at -8 degrees C, and if the specific heat of lemonade is the same as that of water, how many grams of ice does Chris use? Assume there's no heat transfer to or from the surroundings. Answer in 2 significant figures. Okay, let's have this one. Why don't you guys work on this one in groups here? This is probably the most challenging problem, but let's see if you can figure it out in a group. And so we'll do breakout rooms here. Let's say. Let me know if you have a preference. Yeah. So let me do breakout rooms. And we're going to go, let's see, we have 17 people. So we'll go with 4 rooms. Okay. All right, let me know if that works out. Well, we'll try to solve this problem, number 114, as a group here. See how it goes. Okay. So I'll let you guys work on that. Let me know if you need any hints or anything. All right, so how many grams of ice did you guys get? Were you guys able to finish it? I should have checked before I closed the rooms, but. I'm assuming people were able to finish it, so. But let me know. 33.5 grams. All right, 36 grams. Okay, anybody else? 35.5. Okay, that sounds like 30. Well, they said to 2 sig figs, so 35.5 would round to 36. But usually I carry extra digits, so 35.5 is fine. But normally I'd subscript the half, but that sounds like what people got there. So so at least for peer review, it's correct, you know, or it seems to be correct. Okay. Well, anyway, I posted that as a quiz, so that's going to be quiz 13. You could upload it as a group for the on Canvas sometime when you get a chance to upload it. Do you want me to go over it? All right. Yes. Okay, we can go over it. Let's see. Take a look. All right. So we have two things happening here. In Chem 1A, what you'll do is you'll label it, like for example, you know, system and surroundings. That way we can keep track, you know, of the heat. The heat, you know, is conserved, and so it's only exchanged. And so normally what we do is we say, okay, if the system loses heat, the surroundings gain the heat. If the surroundings lost heat, then the system gained the heat, because you know the energy is not going to disappear, it's going to just be transferred. And so normally what we do is we label these like that, but I'm just going to call it the ice and the lemonade, you know. And so whatever heat the ice gained was the heat that the lemonade lost, you know, or whatever heat the lemonade lost. The lemonade has to lose heat because we want it to cool down. It's going to be the heat the ice gained. And so normally when we start off a problem like this, and like say Chem 1A, I would look at it in terms of that, the system and surroundings. Here we're just, you know, in Chem 1A we'll have mixtures of things, you know, and a combination of things, so we have to add up. Here we only have two things. And so we'll just say is the lemonade has to cool down. And so the lemonade is going to lose heat. And so we'll call this Q the lemonade. And where does that heat go? Well, that heat's going to be absorbed by the ice. And so this is going to be Q of the ice. But it's not just the ice, you know. The lemonade is going to cool. And so we want the lemonade to cool from what to what? So lemonade is going to cool from 23 degrees C down to 5 degrees C. So lemonade cools from 23 degrees C to 5 degrees C. And all that heat's going to be absorbed by the ice. Now, to make these equal, I have to change the sign, because when heat is absorbed, it's positive. When heat is lost, it's negative. And so I have to throw a negative sign here to change whatever the sign this comes out to. This sign's going to come out to positive, and to make them equal. And so this is the first law of thermodynamics. First law of thermodynamics is Q of the system is equal to minus Q of the surroundings. And so whatever you call the system, you can define the system any way you want, but whatever heat is gained or lost by the system will be heat that's lost or gained by the surroundings. And to make them equivalent, we need to just change the sign there. And so this is another statement of the first law of thermodynamics, that energy is neither created nor destroyed. Now, the way the ice is going to work is this. We have the ice at -8 degrees C here. And so the first step is we need to warm the ice. And so this will be ice warms. And the ice warms from -8 degrees C to 0 degrees C. That's as hot of ice as you're going to get. You can't get ice hotter than 0 degrees C because then it starts to melt. And so what's going to happen next is the ice melts. Ice melts. And so the ice melts, that's just going to happen at 0 degrees C. And we're going to melt all the ice. You know, ice melts at 0 degrees C. The temperature doesn't change here. But once we melt all the ice, it's still too cold because Chris doesn't want 0 degrees. Chris wants 5 degrees. And so what we have to add as a next step is the ice water warms. Ice water warms. And the ice water is going to warm from, it's going to go from 0 degrees C up to 5 degrees C here. And so all the heat lost by the lemonade is going to be heat that's absorbed by the ice doing this, or all the heat that the ice absorbs, that is in warming up, then in melting, and then in warming up the ice water, or the melted ice, is going to come from the lemonade. And so this is the first law of thermodynamics here, you know, where we conserve that. Now, when an object warms or cools, then we know what it is. It's just mc delta T. Now, this is going to be the mass of the lemonade, the specific heat of the lemonade, and delta T for the lemonade. And so that's the first term. And so we got to figure out how much heat the lemonade has to lose. We can figure out how much heat the lemonade has to lose by just plugging everything in here. And so the mass of lemonade is 175 grams. The specific heat of lemonade, we're going to make an assumption, and we're going to assume that it's about the same as water. And so if it's about the same as water, we have water is memorized at 4.18 joules per gram degree C. And then delta T, well, the temperature has to drop. So it's going to be minus, and how much does it have to drop? It has to drop by 18 degrees. So it's 5 degrees minus 23 is going to give us minus 18 degrees Celsius. And so how much heat did the lemonade have to lose? So we can calculate that here. The lemonade is going to have to lose 175 times 4.18 times 18. So 13,167 joules. Well, that's kind of a hassle. So let's convert it to kilojoules. 13.167 kilojoules of heat. And this is heat loss, so it's going to be negative because of the negative 18 here. This is negative 18. Okay, all that heat has to be absorbed by the ice here. And so all three terms here. And so the ice warms. Well, the ice warms, whenever we have warming or cooling, it's mc delta T. And so how much ice do we have? Actually, we don't know how much. M is unknown. But we do know what C is. This is going to be the C for ice and delta T for ice. And so we do know what these two terms are here. Delta T for ice is going to be plus 8 degrees C. Okay, then ice melts. This is going to be M times delta H of fusion. Delta H of fusion, we know that, that's 333 joules per gram. Plus, okay, ice water warms. Okay, so we know how much ice water is going to be. It's going to be the same mass, you know. Mass is not going to change. And then the ice water warms, it's going to be C of water, and or ice water. times delta T. And delta T for the ice water is plus 5 degrees. This is going to warm up by 5 degrees C. And so the problem is we don't know what M is. So what we're going to do is we're going to factor out M here. And so I'll factor it out here. So this is going to be C of the ice. A C of the ice is 4.18 joules per gram degree C times the delta T of ice. Delta T of ice is 0 minus a minus 8 is plus 8 degrees C. 8 degrees C. All right. Plus, okay, we're factoring out the M. So delta fusion of ice is 333 joules per gram. Okay, plus, okay, factoring out the M, we got the specific heat of water, 4.18 joules per gram degree C, times delta T of water. Delta T of water is plus 5 degrees C. Here. Times M. And so let's go ahead and calculate this part here in the parentheses. And so this is going to be 4.18 times 8 is 33.44 plus 333 is joules per gram plus, okay, 4.18 times 5. So let me do parentheses. 4.18 times 5, close parentheses, 20.9 equals 387. Okay, this comes out in joules. So this is going to be 0.38734 kilojoules per gram. That's a mass, times mass. And then solve for the mass. And so what we're going to do is divide both sides by this term here. That's going to cancel out the kilojoules, and then we'll invert and multiply, and that's going to give us grams. So let me flip that over, times 13.167 equals. Now, let me do that one more time. I gotta screw up that calculation. One thing I have is the sign, you know, oops. The sign, I'm gonna get a negative grams. Well, negative grams of ice is impossible. So I screwed up the sign somewhere. And where I screwed up the sign is I forgot to carry the negative sign down. So this whole thing has to be negative. Here. And this whole thing has to be negative. And this is going to give me a negative here. And so it's negative 13.167 divided by negative 0.38734. And so I get 33.993. Actually, how many sig figs am I allowed? I'm allowed 2 sig figs here. And yeah, we're going to go with 2 sig figs, although this might change it. So 34 grams of ice. Oops, yeah. You're right. The specific heat of ice is not 4.18. The specific heat of ice is 2.06. I made the mistake there. And so this is not water. It should be 2.06 for ice. 4.18 is for water. I don't know what I was thinking. I'm just going to change this term here. So let me redo that. Thanks for catching that. So that's going to be 2.06 times 8 times 333, or not times, plus, times 1 equals plus 333 plus parentheses 4.18 times 5, close parentheses. 20.9, 370.38. 370.38 joules. So I'm going to convert that to kilojoules, 0.37038. Okay, and then do this subtraction. So let me flip this over, times 13.167. 35.5. And so my mass comes out to 35.54 grams of ice. To 2 sig figs, this would be 36 grams of ice. That's what they're after, 2 sig figs. And so this is where peer review worked, you know, everybody got 35.5, 36, except me. I didn't. And so in that case, peer review process would have worked here, because the majority of the people were getting. That's assuming that, you know, the majority of the people weren't wrong. You know, if the majority of people are wrong, then it's wrong. Let's see how the book did it. That's assuming the majority of people are right. So looking at the book, let's analyze. So this is the heat lost by the lemonade, is the heat gained by warming the ice. So this is warming the ice, this is melting the ice, and this is warming the melted ice water. So they did it the same way I did it. This is 35.5. Okay. The thing they didn't do is they didn't keep track of the sign. This is not good. In Chem 1A, you have to keep track of the sign, you know. Although they did energy lost, you know, energy. They're doing absolute value of energy here. That's okay. You know, if we say energy lost is equal to energy gained and then just call energy, that's okay. But when we do calculations, then the sign does have meaning, you know, as far as negative and positive is losing and gaining. That way we don't have to say lost or gained. You know, if we want to make this equivalency, then we have to write here. They would have had to written, if they wrote it like this, then it'd be okay. If they wrote this as lost, and so whatever joules this comes out to, grams cancel, degrees C cancels, that leaves us with joules lost. And then the same thing here, this is going to be joules gained. If we write this, then we can get rid of the sign, you know, but we need to keep track of it. Okay. For Chem 1A, it's better just to write the sign in because the calculations, and then at the end, you can get rid of the sign. You can get rid of the sign by saying lost rather than having negative or gained. You know, just leave the sign as positive. All right, any questions on this? All right, let's move on here. That's the end of chapter 15. So I got to move on to 16 and 17. I want to do 16 and 17. Fortunately, 17 is not too long. 16 is a bit long, but not terribly long. So chapter 16 deals with solutions. So we're looking at pure liquids there. Now solutions are going to be homogeneous mixtures. We could have solid solutions and liquid solutions and gaseous solution. Air would be an example of gaseous solution. Alloys would be an example of solid solutions. And aqueous solutions are an example of liquid solutions, but they don't have to be aqueous. They could be non-aqueous too. So here's mixing up a solution, you know, aqueous solution of copper 2 sulfate. So here's some crystals of copper 2 sulfate. This is the crystal lattice structure here. This isn't a very good lattice structure. Oh, this is not sulfate. Sulfate has a tetrahedral shape. This is copper 2 chloride, sorry. Copper 2 chloride, we can dissolve in water. It's soluble. Chlorides are soluble except for silver, lead, and mercury. And so this is an aqueous solution of copper 2 chloride. Now, when you look at the copper ions, you know, the cations are smaller than the anions typically. So chloride's over here. If you look at copper 2, it's surrounded by waters. It's surrounded by the oxygen end of the waters because oxygen ends are the negative end of water. That's going to help stabilize it. This is called a hydration sphere. And so the waters aren't fixed on there. The waters can be exchanged, you know, but it's surrounded to help stabilize the ion. And the chloride ions are stabilized by having the hydrogen ends or the positive ends of the water molecules hydrating it. And so these are called hydrated ions, and the hydrated ions help stabilize the ions in solution. And so you think, you know, how lattice is strong. You know, the melting point of copper 2 chloride is quite high. You know, and so how can water just break it apart? Well, water breaks it apart by help stabilizing the ions as hydrated ions here, but still you think the ionic bonds are stronger. So there's another driving force in nature which we hadn't talked about, which is called entropy. Entropy is another thing that nature goes towards, and entropy is a measured disorder. So spontaneous processes, that is, driving forces, favor going to more disordered systems. So this is fairly concentrated here. You can see kind of a deep blue color. If it's dilute, it'd be a lighter blue, you know, like this. This is more dilute, it looks like. Some copper. Copper gives the blue color to the water, the copper 2 ions. This is the reaction of copper metal with silver nitrate. And so you can see the silver crystals precipitating on there. Initially, when the silver crystals precipitate, they look black, but these look silver because the crystals are getting bigger. You can see the silver crystals here. Silver crystals have a dendritic pattern. You know, they form like these tree-like crystals. And these are big crystals of silver here, you can see. So the copper is being eaten away. This is a copper wire, this coil. So you can see we're growing more silver here, and the copper, more and more copper is getting oxidized to form copper 2 ions. So the color is getting deeper. So this is just showing a more concentrated solution. This is imaging using, you know, X-rays. And so they put I had this done before. I had this done 2 ways. One, X-rays. Good X-ray absorbers have a lot of electrons. And so if you want to absorb light, you want lots of electrons because electrons like to absorb light. They get excited, you know, and so you want things with a lot of electrons. That's good. And so what has a lot of electrons that's not radioactive? Well, lead. Lead has a lot of electrons and it's not radioactive, but unfortunately it's toxic. And so if you want a good contrasting agent, you could eat some lead salts. You know, if you eat some lead salts, they got a lot of electrons, but people don't want to eat lead salts, even though they aren't that soluble. So as an alternative, a barium. Barium also has a lot of electrons. And so barium salts, but barium salts are also toxic. But barium sulfate isn't very soluble. And so this person had a suspension of barium sulfate, and the barium absorbs X-rays pretty well, so it provides good contrast here. And so I had a barium sulfate cocktail. Barium sulfate's toxic, but it's so insoluble. You know, the solubility of barium sulfate is very low, so it wasn't that toxic. There wasn't much free barium. The barium was locked in the lattice like this. You know, barium ions were locked in the lattice. If the barium ions were free, then the barium sulfate would have been pretty poisonous. And so they don't give you barium chloride because that would be pretty poisonous. They give you barium sulfate and you drink it as a sludge, basically. That was the first contrasting agent. The second contrasting agent I had was iodine. It's just I2, elemental iodine. Iodine has a lot of electrons, but I had an allergic reaction to iodine. You know, so I can't take the iodine anymore. Okay, so this is pretty low solubility. Sodium chloride is high solubility. This is a saline solution for IV trim. What's 0.9%? 0.9% is a concentration of this, but that 0.9% is what we call mass volume percentage. It's 0.9 grams per 100 milliliters of solution. So that's normally a percentage would be like 0.9 grams out of 100 grams, but this is 0.9 grams out of 100 milliliters. And so we call that a weight volume or mass volume percentage. That's what this is called an isotonic solution, because that's the same concentration as your blood, except that your blood doesn't consist of salt. Your blood consists of other things. It essentially has the same concentration, which is important for certain things. Let me do something real quick here.
When moderately concentrated solutions.
We can have, you know, solubility. Solubility is the maximum amount that you can dissolve. So the maximum amount of sodium chloride we can dissolve is not 0.9 grams. This is only 0.9 grams in 100 milliliters. You can dissolve up to 36 grams of salt in 100 milliliters. However, if you tried to dissolve 37, so we could go all the way up to 36% mass to volume. Obviously, you don't want that because it would be way too salty. But you can't have 37%. You can't have 37% because that would exceed its solubility. It'd be saturated. This becomes saturated at 36 grams. So this is still fairly dilute. You know. This is what we call supersaturated. What happens is if you take hot sodium acetate and you cool it down, the crystals don't form so easily. And so hot sodium acetate solution, you can dissolve lots in there because, you know, you can dissolve more sugar in hot water than in cold water. And so let's say you saturate some hot sugar water and then you cool it down. When you cool it down, it becomes less soluble. And so as you cool it down, sugar should start crystallizing out, but sometimes the crystallization process is sluggish. Crystallization is going to require 2 steps. When we think about crystallization, we think about nucleation. So a little baby crystal has to form. It's not as easy as you might think. You know, how do you form a little baby crystal? Usually little baby crystals grow on dust or little or scratches in the glass or impurities or something, some surface that the baby crystals can start to nucleate, to form. And then the baby crystals grow. And so, well, the 2 processes are nucleation and growth. And sometimes nucleation is very sluggish because, especially for something like sodium acetate, because acetates have a weird trigonal planar shape. And that weird trigonal planar shape means that sometimes it's just not in the right position to crystallize. That weird trigonal planar acetate ion has to be in the perfect position in order to crystallize. And so that means nucleation is a little bit sluggish. Excuse me. So what happens is this. You got hot saturated sodium acetate that you cool down. When you cool it down, it should be crystallizing out. Because you got too much sodium acetate in there, but the crystals are having a hard time nucleating. And whenever you have crystals that are having a hard time nucleating, you can give them a seed crystal. A seed crystal gives it a template, you know, and once it has that template, then it can rapidly grow. And so what they're doing here is this used to have no crystals in it, and it's cooled down. It used to be hot, saturated sodium acetate. They cool it down, and it should have precipitated out, but it's not. And so they drop in a little seed crystal in here, and that little seed crystal provides a template for the crystals to grow, and then the crystals rapidly grow. And so this is pretty spectacular, happens very rapidly. Let me see if this was the video.
When moderately concentrated solutions containing silver ions and chloride ions are mixed. When moderately concentrated solutions.
Let me turn down the volume. This is not really, I mean, in a way this is super saturation, but in a way it's not. This is just a straight precipitation.
Solutions containing silver ions and chloride ions are mixed. The resulting solution is supersaturated with silver chloride. A precipitation reaction occurs until the system reaches equilibrium.
This
In
one,
this model, the red and white molecules are water. Chloride and silver ions, gray and green respectively, are in solution. When they encounter each other, they bond and bind with other silver chloride molecules that have precipitated from solution to form the solid.
this is not really supersaturated because it immediately precipitates. Supersaturated means there's sluggish nucleation, and so no precipitate forms. So if they're adding drops on this and no precipitate form, then that's supersaturated. But you can see here that crystals formed immediately. Over here, there are no crystals that were forming, so they had to add a seed crystal. Here, if I added the drops here and no crystals form, and then I add a seed crystal in there, and all of a sudden, boom, the whole thing fills up with crystals, then that's a different story. Then I believe that's supersaturated, but this doesn't look like it's becoming supersaturated. And so let's see. I'm surprised the book didn't put one for me to use. But sodium acetate is a classic example because sodium acetate crystals are hard to nucleate because of the weird shape of it. And so let's look at sodium acetate super saturated demo. This is the sodium acetate mountain here. So this wants to crystallize, this wants to precipitate, but it's having a hard time nucleating the crystals. Fast forward this. All right, so there's some seed crystals. The seed crystals are going to provide a template to help nucleate and grow. Actually, it doesn't have to nucleate now that it has seed crystals. And all it has to do is grow. So that's a supersaturated solution. Okay, going to pour the supersaturated solution on the seed crystals. That's not freezing there, that's precipitation. That's solutions at room temperature. And you can see how supersaturated it was. There was way too much solid dissolved in there. It was just having a hard time nucleating and growing. You can see the crystals starting to grow into the Erlenmeyer flask there. So, what was it? Sodium acetate's a very popular one. Lots of videos of it. Yes, it's easy to make supersaturated. So first you got to dissolve it in hot water and then cool it slowly. Sometimes when you cool it, you know, there's dust or something and it crystallizes. Other times it doesn't. So that's the person dropped a seed crystal in there. And you can see once the seed crystal was dropped in there, boom, the crystals start to form rapidly. There it is. 4 times speed. Let's see one more. There's a sea crystal. Looks like they attached the seed crystal to some stick there. You can see the crystals growing out, radiating. And these form needles. Long, thin crystals. Okay. Move down. They're just using their fingers for seed. Sodium acetate's not that toxic. This is fine. So the fingers are being used for crystals to nucleate and grow. There. Okay. Now, some things they have a finite solubility, like sodium chloride, 36 grams per 100 milliliters. Other things are infinitely soluble. The things that are infinitely soluble are called miscible. And so there's no limit. And so, like, for example, carbon tetrachloride and octane, I can mix those in any proportion. You know, these are miscible. Miscible just means infinitely soluble. Alcohol and water, like methanol and water, are infinitely soluble in one another. They're so similar. The same thing, octane and carbon tetrachloride is similar in the respect of their induced dipole forces. Both of these are nonpolar. However, things that don't mix in any proportion, like gasoline and water, these are immiscible. Immiscible. And so these don't mix. So we'll throw in 2 layers, a gasoline layer and a water layer.
Why don't oil and water mix? The hydrogen bonds between water molecules are too strong to be broken in order to produce a relatively weak interaction between water and the molecules in the oil. Thus, water excludes oil from entering the aqueous phase.
Yeah, hydrogen doesn't want to make, water doesn't want to make room for the gasoline. Each gasoline, if you say gasoline's octane, you know, something like this, then you have to break apart a lot of water molecules to fit a gasoline molecule in there. Gasoline is actually a mixture. It's not pure. Like this looks pure. Actually, no, it doesn't. This is longer chain. Do you see the zigzag chain of carbons? So zigzag, zigzag. This is all tetrahedral. This is a 4 carbon. This is a more than 4 carbon here. So this is a mixture of hydrocarbons.
Why don't oil?
Some things will have a limit, like sodium chloride. I said sodium chloride solubility is about 36 grams per 100 milliliters. And so here, why would sodium chloride even dissolve? I mean, you got to break apart the ionic lattice. So one, we have to break apart the ionic bonds. That costs a lot of energy. These ionic bonds are pretty strong. You know, sodium chloride has a pretty high melting point. What do you get in return? Well, we have to break apart the water. But what we get in return are called ion dipole attractions. Ion dipole attractions are like intermolecular forces, except it's a full charge. This is a full negative charge being attracted to a partial positive charge on water, delta plus. So delta plus on water being attracted to a full negative charge here. This is a full positive charge being attracted to delta minuses on water. And so the ion dipole attractions can be even stronger than hydrogen bonding interactions, because hydrogen bonding interactions are unusually large delta plus. It's an unusually large delta plus because it's a partially exposed proton, but a full positive ion is going to have a higher charge than a partially exposed proton. And so this can, but the partially exposed proton is smaller. So there, you know, the size is another factor, but you know, this is a greater magnitude of charge than delta plus on water. So these ion dipole attractions can be very strong, you know, very strong. When we compare the strengths here to the hydrated ions versus the lattice, it's almost comparable. It's about 5 kilojoules difference. So this is the lattice, the ionic lattice is more stable energetically by about 5 kilojoules per mole compared to the hydrated ions. And so, but that 5 kilojoules per mole is overcome by something called entropy. You know, entropy is driving this here to take care of the rest. All right, this is how the solution process here. And so the water molecules are going to collide and break apart the lattice. So this is what's happening here. The water molecules are colliding and breaking apart the lattice. This is some salt crystal here, let's say. It doesn't have to be a salt, it could be a molecular crystal. And so initially what we have is in the solution process, or this is also called dissolution, or the solution process. Dissolution. The first step here is the dissolution or step here, or the dissolving. Dissolving. Here. So net we have dissolving. This is just, you just dump these crystals in here. But once we get some ions in there, what happens is the ions can strike the surface and stick. If the ions strike the surface and stick, then that's called crystallization or precipitation. We'll call it crystallization. Dissolving is also called dissolution. And so normally we just say dissolution and crystallization. Crystallization is also called precipitation. So what happens is in a saturated solution, this is a saturated solution. Once we've reached saturation, then there's no more change macroscopically. But there's change at the particulate level. That is, dissolution never stops and crystallization never stops. It's just the rates are equal. So the dissolution rate is equal to the crystallization rate. And then therefore we end up with a dynamic. Dynamic is things are going in circles, equilibrium. But you know, there's no net change, no net macroscopic change here. It's interesting because if we have a saturated solution like this, you watch the crystals over time and you see new crystals form, you know, and old crystals disappear. And so it's continually occurring. It's going in circles and cycling like this. Just churning. So yeah, some things will reach the saturation limit, you know, other things won't, like miscible species won't. Miscible are infinitely soluble, so they'll never reach saturation.
Professor, it's break time.
Is it break time? Actually, no. Did we start at 2:05? Yeah, five minutes, I think we'll do break time. Unless you want to break now. We could break now. Maybe it's good to break now. Let's break now. My mouse is not working. So we'll go on break, 15-minute break, starting now. Okay. I got to repair my mouse. Not sure why it's not. just use my mouse. Oh, I see why it's not working. My pen over there. Okay, so break time. I'm going to pause the recording. All right, so this is the solution process or the dissolution process here. So what dictates when we saturate the solution? You know, some things, very little dissolves. Some things very little dissolves because the crystals are so strong, the lattice is so strong, so very little dissolves. Other things, a lot dissolves, but there are different factors that influence it. Factors such as hydration, you know, the smaller the ions, the better hydrated they are. The bigger the ions, the more difficult they are to hydrate. And the lattice energy, the stronger the lattice, the harder it is to dissolve. The weaker the lattice, the easier it is to dissolve. And sometimes those run counter. Weaker lattices usually consist of big ions. And so you might be able to break apart the lattice easily, but you can't hydrate the ions as well. You know, and so there are trade-offs there. And so let's look at some factors that influence solubility here. And the factors that determine the strength of the intermolecular forces within the solute. The solute is like the crystal. And so it could be bonds, like the bonds in the crystal. And so this is the sodium chloride we call the solute, the water we call the solvent. The solvent's the major component, the solute's the minor component. In this case, it would be salt crystals or salt. And so how strongly held are the solute? The solute could also be a liquid, like ethylene glycol here. When we look at ethylene glycol, it's an alcohol and has hydrogen bonds. Okay, so the strength of the intermolecular forces within the solute, within the solvent. The solvent, if it's water, is just hydrogen bonds, and between the solute and the solvent, which would be the hydration spheres. In this case here, we can take a look. If we take a look at ethylene glycol is an alcohol held together by hydrogen bonds. Water is held together by hydrogen bonds, and ethylene glycol and water will be held together by hydrogen bonds. And so ethylene glycol is miscible in water. You know, essentially you could dissolve an infinite amount of this because it's all hydrogen bonding. We're breaking hydrogen bonds, and we're forming hydrogen bonds. And so it's all kind of the same. So it's like mixing water with water. When you mix water with water, you're breaking hydrogen bonds, you're forming hydrogen bonds, and you're breaking hydrogen bonds, that kind of thing. So it's all the same. Whereas like oil and water don't mix, because here, you know, you got to break apart the oil molecules, which would be induced dipole or dispersion forces, and you got to break apart the water. Water doesn't want to break apart because the hydrogen bonding interactions are quite strong, and we have to break a lot of those in order to fit an oil molecule in there. So these are immiscible. This is miscible, this is immiscible here. If we look at salts, you know, we have different solubilities for the salts. You know, cesium chloride up here, lithium sulfate down here. You know, cesium's got big. So let's look at the chlorides here. Sodium chloride is stronger than potassium chloride. You know, lithium are less soluble. Lithium chloride, however, is more soluble. Lithium chloride, because the hydrated ions are quite good. This chart we don't have to really understand in terms of that, but the forces are going to play a role. And so some things are more soluble, some things are less soluble. That's it. Okay, the other factors are if we're looking at a gas. So for example, if we're trying to dissolve, let's say, oxygen gas in water, you know, it's going to depend. Oxygen's nonpolar, water's polar, so oxygen's not very soluble. But ammonia gas and hydrogen chloride gas are very soluble in water. So you can dissolve lots in water. But it's going to depend on the partial pressure of the gas over. And so the higher the pressure of the gas, the more gas we can force into the liquid, you know. And so it depends. Like, for example, here, you know, when we look at a soda, the headspace here is not high pressure. The headspace here is just pure CO2. And if it's pure CO2, we got a lot of CO2s trying to force their way into the water. Lots of them. But when we open this bottle, then air comes in. When air comes in, then there's very little CO2 in air. And so all of a sudden, this is super saturated. The soda is super saturated. We got way too much CO2 in the soda. And so as long as this stays as 1 atmosphere of CO2, we're okay. But once air comes in here, then it drops down to less than 1% of CO2. And so this is another supersaturated demo that's very popular. And one thing that helps nucleate crystals is in sodas, menthos. And so menthos is very popular, the soda demo and menthos. So let's see what we can do. Menthos and soda. Let's look at Menthos Rocket. Maybe a Menthos Rocket. This can go quite high. I don't know if this one's the highest. 100 foot. I think this was a fake one.
All right, we're gonna grab Mentos, like 2 of them. Then we're gonna grab tape and stick them to the tape. Like this. 2 of them. Then we will open the Diet Coke and put it like that, but don't drop it. And tape it like this. And then close it. And then you see it's foaming up because of Mentos. Shake it around. You see the Mentos have fallen and the rocket is ready to go. Safety first. And now we're gonna drop it the bottom down on this thing. Let's go. Let's go. 1, 2, 3. That did not work. All right, that was a fail. Let's try it again. And now we're ready to set this.
Well, the Menthos is going to help nucleate the CO2 bubbles, and then it's just making a pressure rocket.
All right, last time it didn't work, but not too tight this time. And see what happens.
Okay, there it goes.
Yes, and that's too tight. Keep the gun.
I guess the cap was too tight, so it couldn't pop off easily. Let me see, there's another one. Let's see if that other one went 100 feet actually, up in the air.
Hey guys, I'm Ben. This is Ben. Today we're on awesome.
We're gonna
You're welcome
fast forward
to
this.
Backyard Science.
Three Menthos. So it's just super saturated. It used to be pure CO2 up here. No, it's not anymore.
Okay. Now it's gonna shake up the.
There it goes. So anyway, that's super saturated solution of soda, which we can have here. And so when you open it, it's immediately going to be super saturated. Here, this is solubility and temperature. Temperature can affect it. So for most salts, they become more soluble in hot water than in cold water, except for a couple, like lithium sulfate actually becomes less soluble. Gases follow the opposite trend. So this is gases. The solubility of gas decreases with increasing temperatures. So this is what this is showing, like lithium sulfate. Gas would decrease in solubility because high temperatures is going to drive out the gas. Whereas high temperatures are going to increase the kinetic energy, which means that you're going to get more forceful collisions with the crystals, which means more will dissolve. So there's a lot of stuff on this slide, but those are all the factors for insolubility. So this is the dissolution process here, I think.
A can of soft drink contains
Or
carbonated
no,
soda
this
before
is
opening.
this is the super saturated. So inside the soda can is going to be pure CO2.
It is open, gas escapes.
The pure CO2 escapes and air comes in. Air barely has any CO2 in it.
The soda is poured into a glass and bubbles for a while. and eventually goes flat.
It'll go flat because there's barely any CO2 being forced back in there. So we don't have it. So it's super saturated, and that's why the bubbles are forming there. Super saturated. Different ways of expressing concentration. So we aren't going to look at it in that much depth. We just know that different things will have different solubilities depending on those factors. Now, what governs this is Henry's law. Henry's law governs gases. Henry's law just says, you know, if you double the pressure of gas, you're going to double the concentration. You get twice as much gas in solution. That's Henry's law. Once we saturate something, it doesn't even have to be saturated. We can talk about concentration. That is the composition of solutions. One way to talk about the composition of solutions is percentage by mass. And so like this is percentage by mass, you know, or weight percentages. 1.08% this by weight, and then 98.85% other ingredients. And so that's percentage by mass. And so normally we have the equation for percentage by mass like this. You know, we say percent of A, whatever A is, by mass is just grams of A over grams total times 100%. And so this is component A over the total mass. This is for water here. If you look at the entire mass of water on Earth, then 97.5% of it is going to be in the oceans, and 2.5% of the water on Earth by mass is in fresh water. Out of the fresh water, out of this 2.5%, 1.72% is in the form of ice caps, glaciers, and snowpack. 0.77% out of this 2.5% is groundwater, and the rest are lakes, rivers, etc. And so here we have the water cycle here. Evaporation, condensation, etc., precipitation. Ocean water, the percentages get mixed up here because this is 97.5% of the total water on Earth. And then in ocean water consists of 3.5% salts or whatever in the water. So out of every 100 grams of ocean water, we have 3.5 grams of salt solution. But oddly enough, the density is still close to just regular water, you know. Ocean water, we just assume the density is around 1. It's around 1.02 to 1.03 grams per milliliter, the density of ocean water. One easy way is if you take this bucket of ocean water and evaporate it, so let's say this were 100 grams, we'd be left with 3.5 grams of solid at the bottom there. There are other ways of representing concentration. Probably the most common way is molarity. Molarity is just defined as moles of solute per liter of solution. And so molarity is defined as moles of solute per liter of solution. That's molarity. Here is a typical way we make it. Let's say this is a 1 liter flask. This is called a volumetric flask here. And this has been calibrated to be it. Oh no, this is 250. This is a 250 milliliter volumetric flask. Then they have some solute here. So they weigh out some solute. It turns out to be 0.0025 moles. They take this 0.0025 moles and then dissolve it to form 250 milliliters solution. And when they do that, they end up with a 0.0100 molar. This is potassium permanganate. It has this purple grapefruit color of solution. Now you have to be very careful when you use volumetric flasks like this. There's only one marking line there in a volumetric flask. And so if we look at this photo down here, this shows a common mistake that's happened. So there's only one marking, and you have to get the meniscus right on the mark. That's why they're using an eyedropper here, so that they don't overshoot it. If they use a squirt bottle like this, forget it. There's a chance of overshooting it's high. So you need to end up at the bottom of the meniscus here, right on that line here. When you do that, then this is the 1,000 milliliters. Then you'd have 1,000.00 milliliters if you were to line it on that mark. This is high precision volumetric glassware. This is pretty expensive stuff. And so that gives you 1,000.00 milliliters. And so it depends on how many moles, you know, or how many grams. You put some grams. This is not obviously Camin 04. This is some other thing. Probably chromate. Chromate gives a nice yellow color like this. There's probably some chromate solution. And if we had filled it right to the mark, although this looks a little below, you know, this doesn't even look right on the mark. I'd have to add another drop or two there. You want it to line right on the bottom of the meniscus. You overshoot it like this, you have to start over. You dump this, clean it, and then start over again. So what other concentration units do we have? We have percent by mass, but not just percent by mass. We also have percent by volume and mass volume. And so this is grams of solute over grams total. You know, grams total is the solute plus the solvent, but if there are multiple solutes, then you have to add all of them together. And so we have percent by volume, which is a V over V percent. A V over V percent is, you know, if you take milliliters of A divided by total milliliters times 100%, that'll give you percent by volume. Or we can have a percent by mass volume, so an MV percent. An MV percent would be like 0.9 grams of sodium chloride for every 100 milliliters of solution. This is the saline solution. And so that would be an example of an MV solution there. So there are more percentages here. Now, if the concentrations become very low, then we use other ones, not part per 100, but part per million, part per billion, et cetera. And so we could have ppm, ppb, even part per trillion, et cetera. Then we have molarity. Molarity is a big one. We also have something called molality. A molality is not liters, it's per kilogram. A kilogram and a liter are about the same, but not exactly. The advantage of molality is it's temperature independent. Temperature independent. The mass doesn't change with temperature, but unfortunately volume changes with temperature. And so this shows some temperature dependence. Some temperature dependence. That in other words, you could have a 1 molar solution at room temperature, but you know, if you cool it down or warm it up, it's no longer 1 molar. Its molarity changes a little bit because the volume expands with temperature and contracts with temperature, you know, depending on if you warm it or cool it. We have something called normality, but normality is something called equivalence. We're not going to deal with that. We're just going to look at these percentages by mass. This is an M over M percentage. By volume, by mass to volume, or parts per million or parts per billion. This is part per 100. Molarity and molality, those are all important here. One thing we do is we like to buy concentrated solutions because it saves on shipping costs and other things. So we like to buy the concentrated stuff and then dilute it, you know, so you buy concentrated soap, you just dilute it. That way you can save some money. So we do something called solution dilution. We just add water. So this is the concentrated stuff here. Concentrated. So we have a lot of solute and not much solvent. And this is the diluted stuff here. We have the same amount of solute, 1, 2, 3, 4, 5 solute particles, but a lot more water, a lot more solvent, and so it's diluted. And so this process is called solution dilution. It's very common because normally we buy stock solutions that are very concentrated, like the HCl, you know, we'll buy at fairly high concentrations and dilute it to what we need here. Solution dilution, we have an equation for solution dilution. You know, molarity 1 times volume 1 is equal to molarity 2 times volume 2. Molarity times volume. Molarity is moles per liter, volume's liters. So the moles of solute at the start is equal to the moles of solute at the end. That's essentially what the solution dilution equation says. The number of moles of solute, what's changed is solvent, you know, the final volume. And so here's a typical solution dilution. This is the way we do a solution dilution. Here they're going to take 100 milliliters of the more concentrated stuff. And so 100 milliliter volumetric flask has been filled to the mark with 0.100 molar. 0.100 molar doesn't seem concentrated, but in this context, it's more concentrated. This is potassium dichromate. And so this is volumetric, so there's a line here. You fill it to the line, and then you pour that whole thing in here. But we don't get all of it. And so there's 100. Well, so what we do is rinse the rest of it in there so we don't lose any of the dichromate solution. Rinse the rest of that in there, and then we fill it to the mark here. And so this would be 100 milliliters to 1,000 milliliters dilution. And so what's the new molarity? So molarity 2, you know, this we'll call molarity 2. This is molarity 1. Molarity 1 is 0.100 molar, the original molarity. So molarity 2 is going to equal volume 1 over volume 2. Volume 1 over volume 2 is called the dilution factor. Dilution factor times the molarity 1. Molarity 1 is 0.100 is given. So in this particular example here, volume 1 is 100.0 milliliters. That's the original volume. Volume 2, the final volume, is going to be 1,000 milliliters. I'm doing this to 1,000.0 milliliters. It's actually 0.00. Volumetric flasks are good to the nearest hundredth, and so it should have been 0.00. 0.00. It's all right. Times the original 0.100 molar. So this is a 100 to 1,000 dilution, or 1 to 10 dilution. This is going to be a 1 to 10 dilution of 0.1000 molar. So it's going to come out to a 0.01000 molar. So 0.01000 molar is the final. So 1 to 10 dilution. Take 1 part original, dilute it to 10 parts final. This is a 1 to 3 dilution. It looks like about a 1 to 3 dilution, I'm guessing. And so this will be 1/3. This is my dilution factor. Take 1 part original, dilute it to 3 parts final. So 1 part original, 3 parts final. This is going to be 1/3 the original molarity, the initial molarity, or molarity 1. And so it'd be a third is concentrated is what we had there originally.
To create a solution by the dilution method, first use a pipette to take an accurate volume of a concentrated stock solution. Add this stock solution to water to create the dilute solution.
That's a
To create
pipette.
a solution by the dilution method, first use a pipette.
This is a volumetric
volume
pipette.
of a concentrated stock solution.
A volumetric pipette's the same thing, except it's a little less dangerous. If we overfill it, we can drain it and then drain it to the line. So we want the bottom of this curved meniscus to line up with this line. This one looks like a 25 milliliter pipette, which should deliver 25.00 milliliters. It's pretty precise.
Add this stock solution to water to create the dilute solution. The The solution concentration depends on the amount of solute and the final
Oops, I didn't want to do that.
To create a solution by the dilution.
Fast forward that. I wanted to show
create a
one
solution
thing
by
here.
the dilution method, first use a pipette to take an accurate volume of a concentrated stock solution.
Oh, shoot. I can't pause it like I normally would.
To create a solution by the dilution method, first use a pipette to take an accurate volume of a concentrated stock solution.
That's pretty, oh shoot, I did it again. Well, anyway, the couple of things I wanted to show, they got that meniscus right on the line. That's good. Before transferring it over here. Once they got it right on the line, transfer it over here. And then right at the end, you might have noticed they touched the tip because there's a hanging drop there. They touched the tip on the inside of the beaker and that drop sat there and they'll wash that in. Then we need to know what the final volume is. This is a problem. They didn't tell us. We know the initial volume because we have the pipette, but what is the final volume? And so doing this in a beaker is wrong. They need to do it in a volumetric flask like this so we can top it off and get the final volume, the desired final volume that we want. Okay, so that's solution dilution. That's a lab technique that's often used. Let's move on to stoichiometry. When we're dealing with solutions like that potassium dichromate solution that they just mixed or the permanganate solution, then we want to know the molarity of that, because if we know the composition in terms of molarity, then that fits stoichiometry quite easily. Because if we have the volume of solution and its molarity, so if we have the volume of the solution and we know its molarity, then we can go straight from liters to moles, which is kind of nice. Versus if we had the percent by mass composition, then we take the volume of the solution, we need to know the density, and to get the grams of solution. Once we have the grams of solution, then we get the grams of solute. Once we get the grams of solute, we can get the grams of, gram to moles of solute. And so a lot more work here if we had it percent by mass, but if we had it by molarity, it's just one step here. And the same thing on the opposite side. And if we have the moles, we can go straight to liters of solution if we know the molarity. Okay, all these other branches we had talked before about stoichiometry. One of the common stoichiometry problems that we set up, so I'll do a stoichiometry problem when we look at the homework, but this is a specific application of stoichiometry. This is trying to get the stoichiometry right on, a stoichiometric amount. And so this is what's called an acid-base titration here. So they put some acid in here and they put some base in here. And what they want to do is they just want to add just the perfect amount of base, a stoichiometric amount of base. But how do you know when to stop? Well, how you know when to stop is they put an indicator in here, phenolphthalein, and phenolphthalein will turn pink at what's called the end point of the titration. That's when you should stop. So you want to go from colorless to pink, then we know we have the right amount of base, and then we can measure it here. This is using beakers, which isn't nearly as precise. So what they're going to use is they're going to use a pipette to pipette the precise amount of acid in here.
When we combine hydrochloric acid and sodium hydroxide, a reaction occurs that produces a salt in water. The reaction is indicated by a change in color.
We're going to do this tomorrow, titration. And a titration, you're usually looking for an unknown concentration. So for example, we don't know the concentration of the acid, the molarity of the acid. And so in a typical titration problem, it's set up like this. We're looking for an unknown, like for example, the molarity of the acid, and the acid is down here. And usually we pipette, 20.00 milliliters, using a pipette to get that acid in there. And so the molarity of the acid is equal to the moles of acid divided by the liters of acid solution. The liters of acid solution are going to come from this 20 milliliters. Let's just convert it into liters, times 1 liter over 1,000 milliliters. We'll get liters. This one's going to come from stoichiometry, from solution stoichiometry. Because we'll know how many milliliters of base we add in there, and if we know the concentration of the base, then we can get the moles of acid and from the moles of base. And so we'll look at a stoichiometry problem in a little bit. So we'll do some stoichiometry using solutions, which is important, the application.
When we combine
Solutions. And then the last sections, this is actually optional, is colligative properties. Colligative means a collection of properties. And what are the collection of properties that we're interested in here? The colligative properties of solutions. One, vapor pressure. When we compare a solution to the pure liquid, the vapor pressure of the liquid goes down. So this is, you know, normally we're looking at the purple liquid here with no red. And so when we're looking at the purple liquid, it's going to exert a vapor pressure here. But if we have solute dissolved in there, it lowers the vapor pressure by kind of disrupting this vaporization equilibrium process or vaporization. That's what it does. And so one of the colligative properties is called vapor pressure lowering. Pressure lowering. That's what this video is about here.
When a non-volatile solute is added to a liquid, some of its molecules occupy surface sites in the liquid, displacing volatile solvent molecules. Because fewer solvent molecules get to the surface, fewer can escape, and the vapor pressure of the solution decreases.
So that's called vapor pressure lowering. So this is comparing a solution. A solution will have a lower vapor pressure than the pure liquid. That is when we have a non-volatile solute. You know, if we have a very volatile solute, then both of those will exert vapor pressure. Two, we have something called freezing point depression. Freezing. That is, if we look at pure water, it freezes at 0 degrees C. But when we look at salts, salt water freezes at a lower freezing point, a lower temperature. So salt water freezes at a lower temperature than pure water. That's called freezing point depression for solutions.
The two large beakers contain ice. Salt is added to the left beaker. Over a time span of 15 minutes, melting occurs in each beaker.
Okay, you can see that there's considerably more melting in the salt one because the freezing point is lower at a lower temperature. So salt water freezes at a lower temperature, whereas water freezes. So salt water is used to make ice cream. You know, it's used to make ice cream because not that, you know, salt water is colder, you know, than cold ice. You know, these could be at the same temperature. The difference is this. The difference is thermal conductivity. You know, what would you rather jump into? Would you rather jump into snow, fluffy, dry snow at 0 degrees C, or freezing ice water at 0 degrees C? You know, and so for me, I'd rather jump in fluffy, dry snow because you're not going to get nearly as cold because of thermal conductivity, thermal contact, and so ice water can get even colder than 0 degrees C, which makes an excellent, you know, cooling. This is like, I was watching a food show and they're talking about, well, what's the secret to cooling, you know, and they're talking about cooling beer rapidly. And so and the secret was so simple, you know, do you use ice or do you use ice water to rapidly cool beer? You use ice water because of thermal conductivity. You don't use ice alone. Ice would is not going to cool it very rapidly. Ice water will cool it, even though ice and ice water are at the same temperature. You know, that's because of not just thermal conductivity, but you know, it's also due to all those calculations we've just been doing. All right, so why is it? Why do solutions freeze at a lower temperature? And so this is trying to describe this theoretically. You know, a purple dye is dissolved in water and the solution is frozen slowly. So there's dye dissolved in here. There's pure colorless ice along the walls of the tube with concentrated solution in the center of the tube. The solvent solidifies as the pure substance, thus pure ice forms along the walls of the tube. As solvent is frozen out, the solution becomes more concentrated and has lower and lower freezing point. Well, that's not so theoretically, but the ice is going to just make it harder to nucleate and grow crystals as well. So maybe that's one line. Okay, the next colligative property, these all dependent on having solute dissolved in solution. And so the third colligative property is boiling point elevation. So salt water boils at a higher temperature. Salt water freezes at a lower temperature. Salt water boils at a higher temperature. So this is called freezing point depression. It's what we just looked at, and boiling point elevation. And so salt water boils at higher than 100 degrees C. Here, that's boiling point elevation.
When a non-volatile
Okay, so let's take a look at some sample problems from the book. That's chapter. Oh, it's chapter, let's see, 4. So we'll go through these kind of rapidly. And if there are questions, we'll stop. Mixtures of gases are always true solutions. That's true. You know, provided there's no chemical reaction. You know, gases form homogeneous mixtures, loss of empty space. Can you see particles in a solution? No, they're too small. Too small. If you could see it, we usually call it a suspension or a colloid. You know, the solutions of particles are very small and permanently suspended. Distinguish between solute and solvent. Salt water. Solute is sodium chloride. Water is a solvent. Sterling silver. The solute is the minor. So copper would be the solute. Silver would be the solvent. This is what's major. Air. Oxygen's the solute. Nitrogen's the solvent. Air. Sterling silver. Silver would be the solvent, and 7.5% would be another metal, usually copper. Would it be proper to say that the saturated solution is a concentrated solution? No. It's not saturated, just, you know, it's just a limit. And so saturated could be very dilute, you know, it just doesn't, you know, you can't dissolve much in there. Or it could be highly concentrated, you know, but we can't say, so no. And so it's not necessarily. What happens if you add a very small amount of solid sodium chloride to each beaker described below? Okay, beaker containing, if you add some sodium chloride, nothing happens. This is solid sodium chloride will sink to the bottom. A beaker unsaturated, that little bit will dissolve. Supersaturated, you're going to precipitate. It'll be like, you know, sodium acetate. Precipitate. Sodium chloride is very hard to make supersaturated. You know, chloride's spherical, sodium's spherical. So having a supersaturated solution of sodium chloride is very hard. That would be very hard to make. 11, in stating solubility, an important variable must be specified. What is that variable and how does solubility of a solid solute usually? Temperature. Temperature is probably the most biggest variable because, you know, temperature can change how much a solid solute you'll dissolve, you know. The temperature. Usually the higher the temperature, the higher the solubility. When acetic acid, a clear colorless liquid, and water are mixed, a clear uniform colorless liquid results. Is acetic acid soluble? Yes. Is acetic acid miscible in water? Miscible means it's infinitely soluble. And my guess is acetic acid is miscible in water, you know, because small acids like that. Let's see what they say. It is also miscible, a term usually expressed. Okay, when two liquids dissolve. All right. Move on. How is it both cations and anions, positively charged ions and negatively charged ions, can be hydrated by the same substance, water? Water has a dipole, so it has positive end and negative end. Explain why the dissolving process is reversible. We have a crystallization, and which is the reverse of dissolving. So they can precipitate out. Describe the changes that occur between the time excess solute is placed into water and the time the solution becomes saturated. Yeah, you got to let it equilibrate. And so dissolution and crystallization. When dissolving begins, crystallization rate is 0, dissolving rate remains constant. As the solution becomes more concentrated, crystallization rate increases, concentration of the solute in solution continues to increase until crystallization rate equals the dissolving rate. At what time during the development of a saturated solution is the rate at which ions move from the aqueous phase to the solid phase, crystallization, greater than the rate from the solid phase to the aqueous? This would be supersaturated, or this is the only case it can be. Okay, they're saying never, but it has to be supersaturated. They're saying development of a saturated solution. Well, we don't know. We could develop a saturated solution from an unsaturated solution, or we could develop a saturated solution from a supersaturated solution. So I don't agree with this answer. Why can't you prepare a supersaturated solution by adding more solute and stirring it until it dissolved? Usually you have to heat it up, you know, to do that. Otherwise, it's hard to get it dissolved. It won't dissolve. The supersaturated solution is unstable, and a physical disturbance such as stirring will start crystallization. Or shaking, you know, like the soda. Why is coffee stirred to dissolve more? Identify 3 ways in which, or speed up, not dissolve more, but speed it up. Identify 3 ways in which you can reduce the amount of time required to dissolve a given amount of solute in a fixed quantity of solvent. 1, heat it up. 2, stir it. 3, heat it up, stir it. 3, I don't know. Let's just see. Crush it. All right. Stir it or crush it. Stirring and crushing to me have the same thing. I always crush it and stir at the same time. Explain how each action, question 25, speeds up the dissolving process. Surface area, etc. Lewis diagrams. Okay. Which of the following solutes do you expect to be more soluble in water than in cyclohexane? A, formic acid. Formic acid should be more soluble in water, you know, because formic acid can hydrogen bond, water can hydrogen bond, and formic acid can hydrogen bond with water. Okay. B, benzene. Benzene cannot hydrogen bond with water. Benzene, the only thing we have is nonpolar or induced dipole. And so benzene and water don't really mix. However, benzene will mix with cyclohexane. The cyclohexanes induce dipole also. And so benzene and cyclohexane will mix with each other. Benzene won't mix with water. Methylamine. Methylamine should mix well with water because methylamine has hydrogen bonding right here. We've got this trigonopyramidamine hydrogen bonding. Tetrafluoromethane. Tetrafluoromethane is tetrahedral. It's nonpolar. So nonpolar, we just got induced dipole. So that'll be more favorable with cyclohexane, which is induced dipole. So they like each other in that case. Explain your choices. And so we just explain in terms of polar and nonpolar, you know, induced dipole and hydrogen bonding. Which compound, glycerin or hexane, do you expect to be more miscible in water? Glycerin is actually miscible in water. Glycerin's an alcohol. Hexane is this stuff here. Do they have hexane? This is hexane, a 6-carbon chain. It's a hydrocarbon. This is induced dipole only. Glycerin is a 3-alcohol, 3-carbon chain. This is very strong hydrogen bonding. This stuff has such strong hydrogen bonding, it's like syrup. You know, this is very viscous. It pours like syrup. And so glycerin should be miscible. On opening a bottle of a carbonated beverage, many bubbles are released and you hear the sound of escaping gas. This suggests that the beverage is bottled under high pressure, yet it isn't. Yet for safety reasons, the pressure cannot be much more than 1 atmosphere. So it's bottled under just normal atmospheric pressure. What gas do you suppose is in the small space between the beverage and the cap? In other words, the head space. It's got to be pure CO2, pure carbon dioxide. That's going to force a lot more CO2. Otherwise, it's going to be flat, you know, and nobody wants to really drink that flat. 33, calculate the percentage concentration by mass of a solution prepared by dissolving 2.32 grams of calcium chloride in 81 grams of water. So this is a percentage by mass. So we need the total mass. Total mass is going to be 81 plus 232 is 83.32. And so that's the total. And then we have the calcium chloride. So we got 2.32 divided by 83.32 times 100% gives us 2.78% by mass. Calcium chloride. How many grams of ammonium nitrate? Oh, here's ammonium nitrate again. So watch out with this stuff, ammonium nitrate. And of course, we don't want any lab accidents. How many grams of ammonium nitrate must be weighed out to make 415 grams of 58.0% by mass solution? So this I just do using dimensional analysis. We just have to know what this percentage means. And so that's very important that we get the right conversion factor for the percentage. Is that a percent by mass? Yes, it's a percent by mass. So what that means is 58.0 grams out of 100 grams. Then we got to figure out what it is. And so this is 58.0 grams of ammonium nitrate per 100 grams of solution. And so we'll use as a conversion factor here. Now, we're going to start off with 415 grams. So we're going to go grams of ammonium nitrate to grams of solution. So we need to invert this. And then we're going to go from grams of solution to milliliters of water. How many milliliters of water? Oops. Okay, so this is going to be a little bit tricky. 415 grams of solution, because this grams is both ammonium nitrate and the grams of water. And so the tricky thing here is if we have 58 grams of ammonium nitrate per 100 grams of solution, that means the rest is water. So 58.0 grams of ammonium nitrate, and we're going to have 42 grams plus 42 grams of water. So we'll have to do one extra step there to figure it out. let's see what they did really quick. Here. So they figured out how many grams of ammonium nitrate. Or 241 grams of ammonium nitrate. And from that, well, we have 415, this is easier, I guess, the way of doing it. They have 415 grams of solution minus 241 grams of ammonium nitrate, the rest is water. And so 174 grams of water, which gives us 174 milliliters of water. Yeah. So that's a good way. Go ahead. Potassium iodide can be the additive in iodized table salt. Calculate the molarity of a solution prepared by dissolving 2.41 grams of potassium iodide in water and diluting to 50 milliliters. So the volume is 50 milliliters. They want the molarity. And so we need the equation for molarity. And then we can try to use something like dimensional analysis to get the units right. And so molarity, our target is we want moles of solute per liter of solution. We kind of have it, except what we have is we have 2.41 grams of potassium iodide, Ki, over 50.0 milliliters of solution. And so if we convert the milliliters to liters, then we'll have the right stuff on the bottom. So 1,000 milliliters per liter. So milliliters. So we got liters of solution. Now we just have to go grams to moles. So we'll go grams of Ki to moles of Ki, and that will give us moles per liter. Punch it out, and we should have the molarity. Iodized salt is sodium chloride mixed with a small quantity of a soluble ionic compound that contains iodide or iodate ion. So let's see what they did here. So they got the moles of Ki and divided by the liters of solution. 0.290 molar. Molarity is given the abbreviation or symbol capital M. So that means moles per liter. Molarity. A student dissolves 18.0 grams of anhydrous nickel 2 chloride in water and dilutes it to 90.0 milliliters. He also dissolves 30.0 grams of nickel 2 chloride hexahydrate in water and dilutes it to 90 milliliters of water. Identify the solution with a higher molar concentration and calculate its molarity. So we got to just go convert from grams to moles. This one's a little bit tricky. We got to convert from grams to moles, but we're going to have moles of this hexahydrate. But each mole of hexahydrate is the same as the moles of nickel 2 chloride. So here, we'll go grams to moles. Now here we're going to go grams to moles. Even though we're using more, we got to account for these 6 water molecules. So the molar mass is quite a bit higher. And so even though we're using 30 grams of nickel 2 hexahydrate, we actually end up with less moles of nickel 2 chloride than this, as all the mass of the water. The anhydrous compound has more moles and this has a higher concentration. Large quantities of silver nitrate are used in making photographic chemicals. Find the mass that must be used in preparing 2.5 times 10 squared milliliters, 0.058 molar silver nitrate. So this one, whenever we are dealing with solutions, this just means 0.058 moles of silver nitrate per liter of solution, silver nitrate solution. And so we got 250 milliliters of that. And so we're going to go from milliliters to liters, liters to moles, moles to grams. Then we can figure out how many grams of silver nitrate we're using. Let's see what they did. Milliliters to liters of solution, liters of solution to moles of silver nitrate, moles of silver nitrate to grams of silver nitrate using the molar mass. And so we get 2.5 grams of silver nitrate. Potassium hydroxide is used in making liquid soap. How many grams would you use to prepare 2.5 liters of 1.40 molar potassium hydroxide? And so how many grams? Well, we have 2.5 liters. So we're going to go from liters to moles, moles to grams, just like the last problem. So liters of solution to moles of potassium hydroxide, pure potassium hydroxide. So moles of solute, moles of pure potassium hydroxide to grams, potassium hydroxide. What volume of concentrated sulfuric acid, which is 18 molar, is required to obtain 5.19 moles of acid? So we want to go from moles of acid to liters. This is 18 molar, is 18 moles per liter. So let's flip that upside down. So moles to liters using the molarity. Flipped upside down, 0.29 liters. If 0.132 molar sodium chloride is to be the source of 8.33 grams of dissolved solute, what volume of solution is needed? So we're going to go from grams of sodium chloride to moles of sodium chloride. From moles of sodium chloride to liters of sodium chloride solution. And so grams of pure sodium chloride to moles of pure sodium chloride, moles of pure sodium chloride to liters of solution. So it comes out 1.08 using these two conversion factors here. This one would be just the molar mass upside down. This would be the molarity upside down. Calculate the moles of silver nitrate in 55.7 milliliters of 0.204 molar silver nitrate. So here we're going to go from milliliters to liters of solution, liters of solution to moles of silver nitrate, moles of silver nitrate to grams. And so milliliters to liters, liters to moles, moles to, actually, sorry, not grams. They'd want just moles. So we'll stop at moles here. Okay, potassium permanganate has an intense purple color, and this is a strong oxidizer. You got to watch out for this stuff. Despite its intense purple color, potassium permanganate is used in bleaching operations. How many moles of 25? How many moles are in 25 milliliters? So here, this is milliliters to liters of solution, liters of solution to moles using the molarity. And so this problem is just like the last one: milliliters to liters, liters to moles, stopping at moles. The density of 3.30 molar potassium nitrate is 1.15 grams per milliliter. What is the percentage concentration by mass? All right, now this one, we need grams of potassium nitrate over grams of solution times 100. And so that's the percentage by mass. So this is going to be more dimensional analysis. So we want grams of KNO3, potassium nitrate, over grams of solution. And then we want to times it by 100%. So what do we have? We don't have grams, we have moles. We have 3.30 moles of KNO3 per liter of solution. And so the first thing is, let's get rid of moles and convert that to grams. And so on the top, we'll go from moles to grams of KNO3. Let's stop there. On the bottom, we want to go from liters to grams. So we're going to go from liters to milliliters on the bottom, liters to milliliters, milliliters to grams using the density here, and stop, and then times it by 100%. So what we do for that. So here on top, they're going from okay. I don't know, they skipped a step here. Oh, they didn't skip a step. They just wrote it weird. Okay, let me just set this one up because they did it weird. And so I need the molar mass of KNO3. Sometimes if you're in a rush, this is something you can just look up.
Sir, it's break time.
Okay. All right, so it's a break time, and let me do KNO3 here. So we'll finish this one right after a break here. Okay, so let's take a 15-minute break. I'm going to stop the recording here.